Hello there and welcome back to the Sleep Science. Tonight your ears and imagination are getting strapped into a lounge chair at the very edge of the universe. It's dark out here, but it's not the sort of familiar darkness you know when you flick off the lights in your bedroom. No, this is the kind of darkness that hums, a velvet backdrop speckled with light that has travelled billions of years just to smack into your retinas. That glow you see? Those little flecks aren't stars. Most are entire galaxies, each a sprawling city of 100 billion suns, orbiting like fireflies in a cosmic ballroom that doesn't even have walls. The part you can see is only a postcard from your tiny balcony on Earth. The rest stretches away into a night so deep that honestly, you probably won't survive the thought of it if you take it too literally. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, drop your location and your local time in the comments. I always love seeing how scattered across this pale blue dot you all are. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You begin by picturing yourself stepping into NASA's control room at night, glowing monitors scattered across the desks, a quiet murmur of data scrolling, satellites whispering home across vast gulfs of space. The people here don't talk about edges the way you'd expect. You might imagine the universe as a giant snow globe and NASA's job is to press their face to the glass and squint into the darkness beyond. But here, at the literal scientific front lines, the edge is more slippery. It's not a wall, it's not a cliff. It's a horizon of possibility, determined by how far light has had time to travel since the universe began. When NASA points its instruments outward, what they're really doing is winding back a cosmic clock, trying to read the oldest chapters still legible in the fading ink of starlight. You wander outside that control room in your imagination, away from the fluorescent glow, into the crisp night. Above you, the Milky Way arcs across the sky like someone spilled sugar across black velvet. Humans have always stared upward at this sight and wondered about endings and beginnings, but NASA has the audacity to actually send up hardware, giant mirrors, antenna dishes, sensors cooled to colder than space temperatures, to snatch photons that have been travelling since the dawn of time. You catch one in your palm, figuratively speaking, a particle of light that has been running non-stop for over 13 billion years, only to finally trip into your hand as if you were its finish line. That's the kind of marathon we're talking about. Of course, your brain starts chewing on the absurd scale. The edge of the observable universe sits about 46 billion light-years away in every direction. Yes, that's bigger than 13 billion because space itself has stretched like warm dough under rising yeast. It means those galaxies you're peeking at have sprinted away even while their light trudged toward us. Historians of science still argue whether the public ever truly grasped the implication of Edwin Hubble's discovery back in the 1920s that the universe isn't static but ballooning outward. That idea didn't just stretch our maps, it stretched our imaginations to the breaking point. NASA's early attempts to look outward were almost laughably humble by comparison. Back in the 1960s, when missions like Pioneer were still fledgling, most of the agency's energy was focused on beating the Soviets to the moon, not plumbing the edge of creation. Yet even then, quirky little side projects hinted at grander ambitions. One of my favourite tidbits, a satellite called Kobe, launched in 1989, wasn't glamorous. It didn't carry astronauts or flashy cameras, but it ended up detecting faint variations in the cosmic microwave background, literally mapping the baby picture of the universe. That afterglow was so significant it earned its creators the Nobel Prize, and somewhere in a corner office at NASA, I'm sure a janitor had to listen to two physicists argue heatedly about whether the map resembled wrinkled curtains or mouldy bread. Now you picture yourself climbing through a telescope like Alice, stepping through the looking glass. You're not looking at a starry dome overhead anymore, but falling into it, feeling the universe peel back like onion layers. The closest stars whip past you, then clusters of galaxies, then voids so huge they could swallow our entire Milky Way without leaving a ripple. You sense patterns at this scale, filaments, walls, threads of galaxies strung like Christmas lights across unimaginable distances. NASA didn't just stumble upon this cosmic architecture, they teased it out of painstaking surveys, scanning one pixel at a time, building maps that look less like astronomy charts and more like some sprawling 3D spiderweb. But let's not kid ourselves. Standing at the edge of the universe is a slippery experience. What you really confront is the limit of time. The Big Bang happened around 13.8 billion years ago, and the radiation from those early moments is still faintly buzzing through your TV static if you happen to miss the signal. Historians still argue whether edge is even the right metaphor. Shouldn't it be horizon instead? After all, we're not talking about a cosmic fence. It's more like being in the middle of an expanding balloon. No matter where you stand, everything seems to be rushing away from you, and the edge is just the farthest you can see before time itself fogs up. NASA's scientists, though, don't let semantics get in the way. They launch telescopes anyway. They park them in cold, dark places, like the James Webb now sitting in its distant orbit, shaded by a 5-layer sunshield thinner than your fingernail. The Webb isn't just a telescope, it's basically a DeLorean with a gold-plated mirror, sending back snapshots of galaxies so young they look like cosmic toddlers wobbling around in diapers. You can almost imagine those galaxies raising an eyebrow at you across billions of years, like, really? You travelled all this way just to stare at us? And here's a cheeky reality check for you. If you squint long enough at those faint red smudges on NASA's deep field images, you're not seeing galaxies as they are. You're seeing them as they were billions of years ago. For all you know, those same galaxies might not even exist anymore. Their stars could have burned out, merged, collapsed into black holes. It's like browsing someone's MySpace page that hasn't been updated since 2004. What you're seeing is a fossil of Po, not the living, breathing present. Still, there's comfort in that fossil light. NASA scientists often describe the work as humbling but also grounding. You might feel small standing under the night sky, but here's the funny twist. Without tiny humans with glass lenses and patience, the universe would never become self-aware of its own edge. It takes squishy brains inside fragile skulls to make sense of infinite darkness. It's a little like ants discussing the architecture of skyscrapers, adorably outmatched yet undeniably trying. And so, as you stand here at the start of our journey, staring into the so-called edge, remember this: every speck of light you see isn't just a star, it's a message, travelling relentlessly through time. NASA's job is to catch those messages, interpret them, and hand them back to you like postcards from the oldest days of existence. Some postcards are crisp and vivid, others are smudged and cryptic. But together they form a collage that says, the universe is vast, ancient, and still unfolding, and you're lucky enough to witness a piece of it. You lean in closer to that postcard of starlight NASA hands you, and suddenly you notice something strange. The image feels less like a photograph and more like a diary entry written in the language of photons. That's because telescopes aren't just cameras on steroids, they're time machines. Every time NASA points one of those polished mirrors into the night, they aren't catching what's happening out there, right now. They were collecting echoes, fossils, reruns of cosmic episodes that played out eons before humans even thought to invent fire, let alone Wi-Fi. The idea is both simple and staggering. Light has a speed limit, about 300,000 kilometers per second. Sounds ridiculously fast until you realize the distances involved. The sunlight that warms your face took 8 minutes to cross the space between our star and Earth. The light from Alpha Centauri, our closest neighbouring system, left 4 years ago. So when you look at it, you're peeking back to 20, which, let's be honest, feels like another universe entirely. Now scale that up. NASA's great observatories look so far that the light hitting their detectors has been in flight for billions of years. By the time it arrives, civilizations could have risen and fallen in the galaxies it came from. Historians still argue whether humans are truly grasping this concept, or if most of us just nod politely and file it under cosmic weirdness. Imagine yourself holding a telescope. Okay, not literally, because a space telescope is the size of a school bus and weighs several tons, but humour me. You aim it toward a faint red smudge, and what you're really doing is cracking open a time capsule. Every photon that trickles into the mirror is like a little courier pigeon carrying a story from the distant past. Collect enough pigeons, and you start reconstructing whole histories. How stars lit up, how galaxies collided, how black holes grew fat and dramatic at the centres of galaxies. NASA's astrophysicists spend their days decoding these messages, which means their job description is basically part detective, part historian, part extremely patient pigeon trainer. You float now in your imagination through the great chain of telescopes NASA has deployed. The Hubble Space Telescope, launched in 1990, was the first celebrity. Its early days were a little embarrassing. Remember that blurry vision problem because of a misshapen mirror? Quirky tidbit. When NASA astronauts fixed it in 1993 by installing corrective optics, it was basically giving Hubble a giant pair of space glasses. Afterward, Hubble delivered the sharpest, deepest images humanity had ever seen. And here's where the time machine metaphor really hit home. When Hubble stared for days at what looked like an empty patch of sky, it revealed thousands of galaxies, each one sending light from billions of years ago. Suddenly, what looked like nothingness was a jam-packed time vault. Of course, not all telescopes need to see visible light. Some listen to radio waves, others to infrared, ultraviolet, or even gamma rays. Each slice of the spectrum carries its own diary pages from the universe. NASA's Spitzer telescope, for example, specialized in infrared, the glow of warm dust and ancient galaxies. It let us peer through clouds that would normally block the view, revealing stellar nurseries where new suns are born. Without Spitzer's Sapiens contribution, our time machine would have had missing chapters. Then you've got Chandra, the X-ray telescope, which spies on violent events like exploding stars and black holes. If Hubble is the refined archivist, Chandra is the gossip columnist. Did you hear what that black hole did last week? Totally devoured its neighbour. You drift through this gallery of instruments, each one adding a layer of temporal depth. Together, they form what NASA affectionately calls the Great Observatories. They're like a tag team of time travellers handing off different pieces of the cosmic puzzle. And just when you think the team was complete, James Webb rolled onto the stage, flexing its enormous golden mirror like a rock star on tour. Its specialty, looking deeper into the infrared than ever before, peeking at galaxies from just a few 100 million years after the Big Bang. For context, that's the universe's awkward toddler stage, galaxies barely coherent, or stars flickering on for the first time. Historians still argue whether Webb's data will rewrite textbooks completely or just slap sticky notes onto them, but either way, the ink is still wet. Here's a joke for you. A photon walks into NASA headquarters. Someone asks where it came from. The photon shrugs and says, "Depends on whether you mean years or light years." It's a dad joke, sure, but it highlights the weirdness. Distance and time are the same currency in astronomy. When NASA says a galaxy is 10 billion light years away, that's shorthand for we're seeing it as it was 10 billion years ago. The actual galaxy today might be 20 billion light years away thanks to the expansion of space, but you'll never know because the photons carrying that update are still on the road, stuck in cosmic traffic. If this makes your head spin, congratulations, you're in good company. Even professionals get dizzy trying to reconcile the numbers. That's why they rely on telescopes as translators. These machines collect ancient whispers of light, amplify them, and turn them into images and spectra we can pass. A single smudge on a detector might encode a galaxy's composition, age, motion, and star formation rate. It's like getting a postcard that also doubles as a DNA test, a weather report, and a historical census. You pause for a moment in this time machine metaphor and let your thoughts wander back to Earth. Think of the oldest thing you've ever held. Maybe a seashell fossil, maybe a family heirloom passed down for generations. Now compare that to catching photons older than Earth itself. NASA's telescopes are the ultimate antique collectors, and they don't even need dusty shelves. Just clean optics, careful calibration, and a whole lot of patience. The quirky part? Sometimes the data looks like nothing more than squiggly lines or heat maps. Yet within those squiggles lies the story of creation itself. You might be tempted to ask, if telescopes are time machines, can they show us the actual beginning? That's the million-dollar question. The answer is sort of. NASA can peer back to the cosmic microwave background, the faint glow from about 380,000 years after the Big Bang. Before that, the universe was too hot and dense for light to travel freely. It was like trying to see through boiling soup. So telescopes can't show you the Big Bang itself, but they can show you the first chapter after the lights came on. And believe me, the wallpaper of that chapter is still glowing all around you, like the faint static between TV channels. NASA scientists, always good sports, sometimes compare their telescopes to archaeological tools. Each photon is like a pottery shard, each spectrum like a fragment of an inscription. Piece by piece, they're reconstructing civilizations of stars and galaxies that lived and died long before humans emerged. And just like in archaeology, debates flare. Historians still argue whether the earliest galaxies Webb spotted should have been possible so soon after the Big Bang. Are our models wrong? Did stars form faster than we thought? Or are we misinterpreting what the time machine is showing us? That's the beauty of science. Every new window opens a fresh argument, and every argument pulls us closer to the truth. As you stretch back out in your chair, the realization settles. Every glance through NASA's telescopes is a kind of conversation across time. We're not just looking outward, we're looking backward. When you see a star explode through Chandra's X-ray vision, you're not witnessing breaking news. You're attending a historical reenactment billions of years in the making. The cosmos doesn't live stream, it reruns. And our telescopes are the VHS players, the Blu-rays, the streaming apps that let us binge-watch creation itself. And here's the punchline. Every time you gaze up at the night sky with your own bare eyes, you're already time-traveling. You don't need NASA's billion-dollar hardware. You're seeing the moon as it was a second ago, Jupiter as it was 40 minutes ago, stars as they were decades or centuries ago. Your retinas are tiny time machines too. NASA just built the deluxe models, the kind with the cup holders and heated seats. So as you sit in this cosmic lounge chair, remember, telescopes don't just reveal the universe, they reveal its past selves, dressed in outfits from billions of years ago, frozen mid-pose. The edge of the universe is really the edge of time, and NASA's greatest trick has been to turn starlight into a time machine that anyone can peer through, as long as they're willing to squint into the dark and wait for the photons to arrive. You close your eyes for a second and picture yourself drifting in orbit, strapped to the outside of a satellite, Earth glowing below you like a marble, and there above, Hubble. It doesn't look like much at first glance, more like a shiny barrel of soup cans bolted together with solar panels sticking out. But Hubble has a kind of quiet charisma, the way a librarian does when they hand you a book that changes your life. That telescope is the grandparent of space-time machines, the one that made humanity collectively gasp in 1995, with a stunt so audacious it was almost comical. The scientists at NASA decided to point Hubble at nothing. A blank patch of sky the size of a grain of sand held at arm's length. A place that, to the naked eye, looked emptier than your fridge the night before payday. They left it staring for 10 straight days, gathering the faintest whispers of light. People at the time thought this was borderline silly. Why waste one of humanity's most powerful tools staring into a cosmic void? Quirky fact, one astronomer actually called the plan a fishing expedition in the dark. But when the images were processed, the nothingness wasn't nothing. It was thousands of galaxies, each containing billions of stars, each one a cosmic metropolis frozen in its ancient youth. Suddenly, that grain of sand became a window, showing that the universe was teeming with far more galaxies than anyone had dared to imagine. Historians still argue whether this single image, the Hubble Deep Field, was the most important astronomical picture ever taken. Some call it the ultimate selfie of the universe. Imagine being one of the first people to see that processed image. You lean over a monitor in a dim NASA lab, sipping lukewarm coffee, trying not to spill it on the keyboard. At first, it looks like static. Then your brain starts to recognize patterns, spirals, ovals, smudges of red and blue. You realize every single speck is a galaxy, and you suddenly feel your knees go weak. It's like opening a treasure chest and realizing the treasure is infinite. The image made headlines, it made posters, it made desktop wallpapers, it made humans feel both impossibly tiny and impossibly lucky at the same time. The thing is, Hubble wasn't even supposed to be this bold. It was designed for lots of general tasks, mapping star clusters, studying the atmospheres of planets, tracking comets, but the deep field gave it a reputation for courage, as though the telescope itself had decided to break character, lean against the cosmic bar and order a stronger drink. From then on, deep became part of Hubble's identity. It followed up with the ultra-deep field in 2004, staring for 11 days into a slightly different empty region, revealing about 10,000 galaxies in an area 1/10 the width of the Moon. 10,000 from one tiny postage stamp of sky. That's when the math really hit home. If this much exists in such a small patch, then multiply it across the whole sky. We're looking at hundreds of billions of galaxies. Your mind doesn't just boggle, it folds in on itself like a cheap lawn chair. Now let's sprinkle in one of those odd tidbits that keeps science from ever getting too serious. When Hubble was first launched in 1990, its main mirror had a flaw so small, just 2 microns, but devastating enough to make all its images blurry. Newspapers at the time called it the $2 billion blunder. It was like saving up for the world's most expensive camera, only to find out it couldn't focus. For 3 long years, Hubble was essentially a punchline. Then in 1993, astronauts aboard the Space Shuttle Endeavour installed corrective optics, basically a cosmic contact lens. And just like that, Hubble went from dud to legend. If anything, that rocky start made its later triumphs sweeter. It was the underdog telescope that blew the roof off our understanding of the cosmos. You float deeper into the idea of those deep fields. Each one is a time slice, galaxies frozen at different stages of their evolution. Some look mature, with elegant spiral arms. Others are clumpy, irregular, messy toddlers who are still learning how to hold themselves together. The farther away they appear, the younger they actually are, because their light left them billions of years earlier. It's like looking at a family photo album where every page is from a different century, yet they're all laid out together. NASA scientists comb through these cosmic scrapbooks, counting galaxies, measuring redshifts, tracing how the universe grew from chaos into complexity. Historians still argue whether the deep field truly proved that galaxies formed earlier than expected, or if it just revealed our models were naive. Either way, the debates keep humming like background static, proof that science thrives on question, not answers. And yes, there's a humorous side to all this grandeur. One astronomer reportedly quipped, after seeing the deep field, "Well, there goes my weekend. I'll be explaining this to reporters until Monday." Another compared the image to a jar of fireflies spilled across the floor. The human brain, after all, scrambles for metaphors when confronted with infinity. You too might find yourself staring at the deep field image online and thinking it resembles glitter glue on black paper. That's the delightful paradox. The most profound photograph in history looks like kindergarten art, yet it whispers secrets from the dawn of time. Pause for a moment and imagine drifting into that image. You shrink down and step across its canvas, hopping from galaxy to galaxy like stones across a river. Each one you pass has its own history of starbirth, supernovae, black holes, and possibly even civilizations we'll never meet. Some of the light in Hubble's deep field left before Earth existed, before the sun ignited, before the Milky Way even settled into its current form. And yet here you are, tracing it with your fingertips through a telescope parked just above your home planet's atmosphere. It's like opening a time capsule only to realize it was addressed to you personally. The cultural ripple of Hubble's deep field was enormous. It didn't just shake the scientific community, it filtered into philosophy, art, even religion. People used it as a meditation backdrop, a reminder of cosmic perspective. Some even joke that it should be printed on motivational posters. Feeling small, you are, but that's okay. NASA's PR team leaned into it, releasing high-res versions, animations, even 3D fly-throughs where you can dive into the field like you're swimming through galaxies. It was less a scientific result than a public service announcement from the universe. Hey, you're not the center of everything, but you're part of it. Congrats! Even now, decades later, Hubble continues to build on that reputation. Every new deep survey adds more data, more galaxies, more faint smudges of light that push the boundaries of what we can see. And yet, despite its successors like James Webb stealing some of the spotlight, Hubble remains iconic, the telescope that first dared to stare into the abyss and found it wasn't empty at all. If telescopes are time machines, then Hubble was the one that gave humanity its first real glimpse of the vast timeline we inhabit, showing us not just the present, but the sprawling, chaotic, luminous past. So as you recline in your imaginary orbit, watching Hubble hover silently against the velvet backdrop of space, remember this. Its greatest discovery wasn't a particular galaxy or star cluster. It was the revelation that the universe, no matter how blank it looks at first, is overflowing with hidden wonders, if only you have the patience to look long enough. And that, in many ways, is the very heart of science itself. You drift back from Hubble's grain of sand miracle, still dizzy from the revelation that emptiness was an illusion, when a new thought slips in. If telescopes are time machines, what's the farthest back we can possibly go? Hubble showed galaxies in their infancy. Webb now teases us with toddler universes, but even those are still late arrivals to the party. Before the first galaxies, before the first stars, before space looked like anything more than a formless fog, what about then? NASA's answer is almost poetic. You can't see the beginning directly, but you can still hear its afterglow. That afterglow is called the cosmic microwave background, or CMB. if you prefer acronyms that sound like radio stations, imagine the universe about 380,000 years after the Big Bang. Before then, it was so hot and dense that light couldn't travel freely. Photons kept bouncing off the electrons like a mosh pit at a concert. But as the universe expanded and cooled, those photons finally slipped free, racing off in every direction. They've been travelling ever since, stretched by cosmic expansion until they're now microwaves, bathing the entire sky in a faint static hiss. You can't see it with your eyes, but tune an old analog TV to a dead channel, and about 1% of that fuzz is the universe's baby photo buzzing straight into your living room. It sounds almost like science fiction. The universe has been whispering its origin story non-stop for nearly 14 billion years, and NASA figured out how to eavesdrop. The quirky detail is that this wasn't even NASA's discovery. Back in 1964, two Bell Labs engineers, Arno Penzias and Robert Wilson, were testing a radio antenna in New Jersey. They kept hearing a persistent hiss, no matter which way they pointed it. They tried everything, even cleaning out pigeon droppings from the dish. Yes, that's the weird trivia part. Cosmic history almost disguised itself as bird poop. Eventually, they realized they'd stumbled upon the faint afterglow of creation itself. For this, they won the Nobel Prize, and pigeons everywhere were redeemed as unwitting participants in the greatest discovery of the century. NASA, of course, took this discovery and supercharged it. In 1989, they launched the Cosmic Background Explorer, or COBE, to map this radiation with precision. When COBE's data rolled in, it didn't just confirm the background existed, it revealed tiny fluctuations, slight warm and cool spots, the fingerprints of the very first structures in the universe. George Smoot, one of COBE's scientists, famously described it as seeing the face of God. That phrase caused quite a stir. Historians still argue whether it was scientific poetry or reckless hyperbole, but either way, the message was clear. These ripples were the seeds from which galaxies eventually grew. Fast forward to 2001, and NASA leveled up again with the Wilkinson Microwave Anisotropy Probe, WMAP for short. This satellite gave us a much sharper baby picture, mapping the universe's background glow to incredible detail. It told us the age of the universe, 13.7 billion years, give or take a cosmic heartbeat. It told us the proportions, roughly 5% normal matter, 27% dark matter, 68% dark energy. In other words, WMAP didn't just take a snapshot, it drafted the universe's birth certificate. Imagine you're at a cosmic family reunion and someone finally brings out the baby album. Everyone gasps. Oh, so that's what little Cosmos looked like before he grew galaxies and quasars. But NASA wasn't done yet. In 2009, the European Space Agency launched the Planck Observatory with NASA as a partner to push resolution even further. Planck's map is the clearest image we've ever had of the early universe, precise enough to show that the cosmos had tiny lumps and bumps, imperfections that made everything we see possible. If the universe had been perfectly smooth, no galaxies, no stars, no us. The fact that it was slightly uneven is the only reason you're sitting here tonight, listening to a sleepy voice talk about it. Imperfection, it turns out, is the mother of creation. Pause here and let yourself feel it. Imagine floating in space with microwave-sensitive eyes, watching a faint glow spread across every inch of the sky. It's not bright, not blinding. It's more like the dim ember of a fire that burned out long ago, still radiating warmth. You realize this is the oldest light you will ever see, a message written when the universe was less than 500,000 years old. That's younger than an infant compared to its 13.8 billion year age now. And yet this infant glow contains all the clues to how the cosmos grew up. Here's a fun aside. If you could actually hear the CMB, what would it sound like? NASA scientists once converted the data into audio. The result? A faint hum somewhere between white noise and a low musical chord. One researcher joked it sounded like the universe clearing its throat. Another said it was less Beethoven, more broken refrigerator. Either way, it's strangely comforting. The idea that creation itself still hums in the background, a lullaby for anyone tuned to the right frequency. Of course, not everything is tidy. Historians still argue over anomalies in the CMB data. There's something called the cold spot, a patch of sky noticeably cooler than expected. Some think it's just a statistical fluke. Others speculate it might hint at something exotic, like the scars of a collision between our universe and another. Yes, you heard that right. The multiverse theory sometimes sneaks in through these little imperfections. NASA, careful as ever, doesn't make wild claims, but the debates keep simmering. Is the cold spot just random noise or a doorway to deeper truths? You lean back in your chair and realise the poetry of it. Hubble gave us galaxies in their ancient youth. Webb gives us stars at their first flicker. But the microwave background is the cosmic placenta, the leftover heat from the very womb of creation. To study it is to study the nursery wallpaper of the universe. The texture of reality before reality looked like anything at all. NASA's telescopes, in this sense, are archaeologists not of bones and pottery but of temperature ripples spread across infinity. And yet, for all its profundity, the CMB has a surprisingly homely side. You could say it's the universe's version of baby photos plastered on the fridge. They're blurry, they're lumpy, and they're a little embarrassing, but without them, you wouldn't know how the kid grew up. You laugh quietly at the thought. Humanity, with all our drama and politics and pizza toppings, owes its very existence to tiny temperature differences in a glowing fog 13.8 billion years ago. That's the kind of perspective that makes traffic jams feel slightly less important. Take another slow breath. Let the hum of that background glow settle into your mind. You realise now that the edge of the universe isn't just a place you can look, it's a sound you can almost hear, a warmth you can almost feel, a memory baked into the very fabric of space. NASA didn't just find galaxies at the edge. They found the afterglow of everything, the proof that we are children of a fireball that still whispers in microwaves. You're still basking in the hum of the microwave afterglow, lulled by the thought that the universe keeps its baby picture taped to the cosmic fridge when another realization tugs at you. All that ancient light is running away. It's not sitting still like a painting in a gallery. The galaxies themselves are slipping farther and farther from each other, like marbles scattered across an inflating balloon. And the person who first broke this news to humanity? Edwin Hubble, an astronomer whose discovery in the 1920s rocked science like a scandal. Picture the world of astronomy a century ago. Back then, people weren't even sure what galaxies were. Some scientists thought those smudges of light in the sky, spiral nebulae they called them, might just be gas clouds inside the Milky Way. Others argued they could be entire island universes, separate from our own. Historians still argue whether the famous Great Debate of 1920 was ever truly settled in that moment. But the clash between Shapley and Curtis, two heavyweight astronomers of the day, set the stage. Then along came Edwin Hubble, tall, meticulous, fond of bow ties, and armed with a telescope at Mount Wilson Observatory in California. What he did was deceptively simple. He studied the light from galaxies and noticed something peculiar. The spectral lines were shifted toward the red end of the spectrum. Like the way an ambulance siren sounds lower when it's moving away, the light from galaxies was stretched out, red-shifted, as though the galaxies themselves were receding from us. The farther away a galaxy was, the greater the redshift. Hubble plotted these distances and velocities on a graph, and the result was a straight line. The universe was expanding. Space itself wasn't static. It was stretching like warm taffy, pulling everything apart. You take a deep breath and try to absorb what this means. Before Hubble's discovery, most people assumed the universe was eternal and unchanging, like a grand cathedral frozen in time. Suddenly, that cathedral had scaffolding, blueprints, and a birth date. The cosmos wasn't a monument, it was a living thing, dynamic and restless. The shock of that realization rippled through physics, philosophy, and even theology. Suddenly, the idea of a beginning was on the table, which made some scientists deeply uncomfortable. After all, if the universe had a beginning, didn't that smell suspiciously like the old creation stories? Historians still argue whether Hubble himself fully grasped the philosophical fallout, but his graphs left no room for denial. Let's pause for a quirky tidbit. Edwin Hubble didn't even win a Nobel Prize for this discovery. In fact, at the time, the Nobel Committee didn't award prizes for astronomy. It wasn't considered real physics. That policy changed later, but too late for Hubble. Imagine discovering that the entire universe is expanding and still being told, sorry, no trophy. It's like inventing pizza and not getting a slice. Of course, once the news was out, people scrambled to make sense of it. If the universe is expanding, does that mean it had a beginning? A Belgian priest and astronomer named Georges Lemaitre thought so. He proposed what he called the primeval atom, or cosmic egg, an idea that would later evolve into the Big Bang theory. At the time, though, many scientists scoffed. Some preferred an alternative, the steady-state model, where new matter was constantly created to fill in the gaps as the universe expanded, keeping it eternal and unchanging. Historians still argue whether this resistance was scientific caution or philosophical stubbornness. It took decades of evidence, including NASA's detection of the microwave background, to finally put the steady-state idea to rest. But back in Hubble's day, the discovery was enough to make heads spin. Imagine standing at a train station, watching locomotives pull away in every direction. At first, you'd think maybe they all just happened to leave at once. Then you realise, no, it's the platform itself that's stretching, carrying you farther from every train simultaneously. That's what space does. Galaxies aren't racing through space. Space itself is expanding, carrying galaxies along like raisins in rising bread dough. This analogy gets tossed around so often in astronomy classes that students roll their eyes, but it's effective. You picture a loaf in the oven, raisins drifting apart as the dough inflates. The raisins don't move by themselves, the dough does the work. Congratulations, you're now imagining yourself as both raisin and bread. The implications are wild. If everything is expanding, then rewinding the cosmic tape means everything was once closer together. Go far enough back, and the entire universe collapses into a singular point of origin. That idea unsettled a lot of people in the early 20th century. Some even accused Hubble's supporters of smuggling religion into science. But Hubble himself stayed cautious. He presented the data without pushing for interpretations, letting others fight about cosmic beginnings while he focused on gathering more redshifts. A bit of dry humour, one colleague called him a man who discovered the universe but preferred to stay indoors. Now, let's fast forward to NASA's role in all this. When Hubble the man discovered the expansion, he had only a handful of galaxies on his chart. A century later, Hubble the telescope expanded that chart to tens of thousands. NASA's space telescopes confirmed and refined the expansion rate, known as the Hubble constant in honour of the man himself. But here's where it gets messy. The numbers just don't quite agree. Using the cosmic microwave background suggests one value, while measurements from nearby galaxies suggest a slightly faster rate. Historians still argue whether this Hubble tension signals new physics or just a mistake in our methods. Either way, it's proof that Hubble's shock still echoes today, keeping cosmologists up at night. You tilt your head and wonder what this means for your place in the grand scheme. If galaxies are all running away, are we at the centre of the universe? Not quite. From any galaxy, the view looks the same. Everything appears to recede. It's not that Earth is special, it's that expansion is universal. You're not standing at the centre of a cosmic explosion, you're riding along on the same expanding wave as everyone else. It's democracy, but for galaxies. Now comes the part where the humour sneaks back in. One popular way to picture this is a balloon with dots drawn on it. As the balloon inflates, the dots move apart. No dot is the centre. Of course, if you actually try this at home, you'll realise the dots smudge, the balloon pops, and you're left with a disappointing mess of rubber. Not the most dignified metaphor, but it works. NASA scientists use it in press conferences anyway, and audiences nod politely, pretending they didn't just picture the universe as a cheap party decoration. Still, that simple balloon captures the heart of the shock Hubble delivered. The universe isn't static, it's dynamic, restless, growing ever larger. It has a history and inevitably a future. Will it expand forever until it cools into silence, or will it someday slow down and collapse? Those are questions for later in our journey. For now, the key is this: the universe is in motion, and we are passengers on the ride. You glance again at that faint glow of the cosmic microwave background, the universe's baby photo, and realise how perfectly it fits Hubble's revelation. The glow is stretched light, redshifted over billions of years by the expansion he discovered. The two stories, Hubble's redshifts and NASA's baby picture, are threads of the same fabric woven across a century of science. Together they tell you, we're not static creatures in a static cosmos. We're part of an unfolding drama, a balloon still inflating, a loaf still rising, and maybe, as you lie there tonight listening to this cosmic bedtime story, that thought feels oddly comforting. You don't need to worry about keeping up. The universe is expanding at every point, and you're expanding with it. Whether you like it or not, you're along for the ride. One raisin among trillions, carried outward by the dough of creation. You sit there still mulling over Edwin Hubble's shocking graph, galaxies scattering like raisins in cosmic bread dough. When NASA drops another bombshell, the dough isn't just rising, it's speeding up. The universe isn't merely expanding, the expansion itself is accelerating, as if some unseen hand is pressing harder on the cosmic gas pedal. The culprit? Something so mysterious scientists had to give it a spooky placeholder name. Dark energy. Now, pause for a second and let that sink in. When astronomers first expected to measure the expansion rate in the late 20th century, they thought they'd see it slowing down. Gravity, after all, is the universe's great party pooper, always trying to pull things back together. Like a tossed baseball slowing in the air, the galaxies should have been tugging on each other, gradually reducing the expansion speed. But when NASA and its collaborators measured distant supernovae in the 90s, those bright stellar explosions that serve as cosmic yardsticks, they found the opposite. The explosions were dimmer than expected, meaning they were farther away than they should be. The only explanation? The universe had been speeding up. Instead of a cosmic baseball, it was a cosmic rocket. Here's the quirky part. The discovery wasn't made by one of NASA's shiny flagship telescopes. It came from ground-based observatories, with NASA contributing crucial follow-ups and satellite confirmation. Two teams raced to publish in 1998, and the result was so shocking it earned the 2011 Nobel Prize in Physics. Yet even today, if you corner a cosmologist at a conference and ask, "So what exactly is dark energy?" they'll probably laugh nervously, sip their coffee, and change the subject. Historians still argue whether dark energy is even the right term. It's not an energy we can measure directly, nor does it behave like anything familiar. It's just a placeholder for something in the equations that makes the universe accelerate. Some think it might be the energy of empty space itself, a constant push baked into the fabric of reality. Others imagine exotic new fields or particles. A few suggest Einstein's equations of gravity might need rewriting altogether. It's like realizing your car is speeding up while your foot is off the gas, and instead of checking the engine, you start suspecting the laws of physics are playing a prank. NASA's satellites, of course, took the mystery and ran with it. Missions like WMAP and later Planck mapped the cosmic microwave background in exquisite detail, showing that about 68% of the universe's energy budget is this invisible dark energy. That means everything we see, stars, planets, gas clouds, you and me, is only about 5% of the cosmic pie. Another 27% is dark matter, which is mysterious in its own right, but at least it clumps and has gravity. Dark energy, on the other hand, seems to be the invisible engine behind the accelerating expansion. In other words, most of the universe is made of stuff we don't understand, and the small slice we do understand includes pizza and TikTok. You lean back and chuckle at the absurdity. Imagine throwing a birthday party and realizing 95% of the guests are strangers you can't even see. They're drinking your punch, they're rearranging the furniture, and yet you have no idea who invited them. That's astronomy in the age of dark energy. We know it's there because of the effect, but its identity remains maddeningly elusive. And then there's the philosophical sting. If the universe is not just expanding but accelerating, what does that mean for the future? It suggests galaxies will drift farther and farther apart until eventually distant ones slip beyond our cosmic horizon forever. Already a samosum light from galaxies beyond about 46 billion light-years can never reach us, no matter how long we wait. Over trillions of years, if dark energy keeps pushing, the universe could become a lonely place. The Milky Way and its local neighbours might merge into one supergalaxy, but everything else would fade into invisibility. Future astronomers, if anyone's still around, might look out and conclude they live in an empty universe, never suspecting the rich cosmos we see today. Historians still argue whether this makes our era special or just a temporary accident of cosmic history. Here's where NASA's current and upcoming projects step in. The Nancy Grace Roman Space Telescope, set to launch later this decade, is essentially a dark energy detective. It says it will map millions of galaxies and supernovae to measure how the acceleration has changed over time. Then there's the Euclid mission from ESA, with NASA as a partner, already hunting cosmic structures to probe the same mystery. Think of them as forensic teams at the scene of a crime, dusting the cosmic walls for fingerprints of dark energy. But the universe isn't making it easy. Every new dataset adds nuance, sometimes contradictions. For instance, one possible explanation is that dark energy is simply Einstein's cosmological constant, a term he once inserted into his equations to keep the universe static, later calling it his biggest blunder. Quirky twist? If dark energy really is the cosmological constant, then Einstein's blunder was actually prophetic genius. Talk about a cosmic plot twist. Historians still argue whether he truly regretted it or just enjoyed the drama of the story. Of course, there are weirder ideas. Some scientists propose that dark energy isn't constant at all. It could change over the time, growing stronger or weaker. Others wonder if it's tied to extra dimensions, hidden realms folded up in space. A few fringe thinkers even speculate that what we call dark energy might be an illusion caused by inhomogeneities in the universe, like thinking the Earth is flat because you're standing on Kansas. Most of these ideas never make it past conference talks and coffee break debates, but the point is, nobody knows for sure. And in science, admitting ignorance is the first step toward discovery. Now, let's drop in a human-scale metaphor to keep your brain from overheating. Imagine you're running on a treadmill. At first, you expect the belt to gradually slow, making your jog easier. Instead, the treadmill starts speeding up and you don't know why. You look around, no one's pressing the controls, the machine just has a mind of its own. That's what dark energy is doing to space itself. The cosmic treadmill is running faster and galaxies are being carried away whether they want to or not. You, standing in your slippers, can only watch the scenery blur. Here's a humorous tidbit to keep it light. One journalist once described dark energy as the universe's credit card debt. It keeps growing, nobody really understands the interest rate. And the final bill will probably arrive the worst possible moment. It's a silly analogy, sure, but it captures the anxiety scientists feel. Dark energy isn't just a puzzle, it's a looming fate. And yet, there's something oddly calming about it too. The acceleration is gentle, stretched across billions of years. You won't wake up tomorrow to find the stars streaking away like a sci-fi warp drive scene. In fact, in your lifetime, the night sky won't change much at all. The constellations will stay familiar, the Milky Way still glowing overhead. The whispers of dark energy are so subtle that only with decades of patient observations, supernovae measured, galaxies mapped, ripples in the cosmic microwave background analysed, do we even notice them. It's the quietest revolution ever discovered. So as you sit here imagining yourself floating through an inflating cosmos, remember, most of the universe is invisible, unknown, and whispering secrets we're only beginning to catch. Dark energy is the faint background hum of acceleration, a mystery woven into the very fabric of reality. NASA didn't set out to find it, but once they stumbled upon the evidence, they couldn't look away. Now, every new telescope is tuned like an ear pressed against the cosmic wall, listening for those whispers. And the whispers say this: the universe isn't just growing, it's rushing ahead into a future stranger than we ever imagined. The whispers of dark energy are still echoing in your ears when a glint of gold catches your eye. You turn and there it is, the newest time machine in NASA's fleet, floating quietly in the cold, a massive mirror shining like a sunrise that never ends. The James Webb Space Telescope. If Hubble was the wise elder who first dared to look into the abyss, Webb is the ambitious prodigy who took the family telescope, added a gold-plated makeover, and drove it straight into the dawn of time. You imagine yourself drifting closer. Webb is enormous. Its hexagonal mirror segments arranged like honeycomb cells, each one covered in a layer of gold thinner than a human hair. The whole contraption sits shielded by a 5-layer sunshade, the size of a tennis court, keeping it cooler than outer space itself. Without that shade, Webb would blind itself with its own warmth. Instead, it stares deep into the infrared, the wavelength of ancient stretched light, the kind that carries stories from the universe's earliest chapters. The first images Webb sent back in July 22 were enough to make even seasoned astronomers choke up. One in particular, the deep field image, looked almost like Hubble's famous shot, but sharper, denser and deeper. Galaxies tumbled across the frame like spilled jewels, some so faint their light had been travelling for over 13 billion years. You look at it and realise you're seeing galaxies that existed just a few 100 million years after the Big Bang. In cosmic terms, that's not even the toddler stage. It's more like catching the universe still in its newborn blanket, blinking awake for the first time. And here comes the twist. The galaxies Webb found weren't scrawny little infants. Some were already surprisingly massive, packed with stars in numbers that should have taken far longer to build. Historians still argue whether this discovery means our models of galaxy formation are missing something, or whether we've simply been underestimating how quickly stars could form in those early days. It's as if you opened a baby book and found a picture of a toddler bench pressing weights. Something doesn't add up, and Webb is gleefully forcing scientists to rethink the rules. Quirky detail: the first batch of Webb images included one astronomer's absolute favourite, Stephan's quintet. A group of 5 galaxies dancing and colliding in a slow-motion cosmic tango. The image looked so crisp that people joked it belonged on a sci-fi movie poster. But it wasn't Hollywood CGI, it was the raw truth of physics on a galactic scale. Collisions like that are how galaxies grow, how stars get churned into new generations. NASA had essentially handed us front-row seats to the most elegant demolition derby in existence. Of course, Webb isn't just about pretty pictures. Its instruments can analyse spectra, breaking light into its component colours to reveal chemical fingerprints. That means Webb can sniff out the atmospheres of exoplanets, detecting water vapour, carbon dioxide, even methane. Imagine pointing it at a planet dozens of light years away and learning whether it has clouds, storms, or perhaps conditions ripe for life. Suddenly, Webb isn't just a time machine, it's a detective, poking around alien kitchens to see what's cooking. One astronomer described the experience as reading the grocery list of an alien world. Historians still argue whether these early detections are reliable, or if we're seeing hints that need confirmation, but the excitement is real. Let's not forget the drama of getting Webb up there. For over 2 decades, it was plagued by delays, budget overruns, and technical headaches. Originally estimated to cost $500 million, the final price tag ballooned to nearly $10 billion. People joked it should be called the Just Wait Space Telescope. Yet when it finally launched on Christmas Day 21, riding a European Ariane 5 rocket, it unfolded flawlessly over weeks, each step as nerve-wracking as open-heart surgery. NASA engineers held their breath through 3 more single points of failure, any one of which could have doomed the mission. And yet, everything worked. It was like watching a magician pull off a trick so audacious you wondered if maybe the universe itself wanted Webb to succeed. Now imagine Webb's view. Its infrared eyes pierce the fog of early time, revealing structures that were hidden to Hubble. You drift through these scenes in your imagination. Passing galaxies shaped like question marks, arcs stretched by gravitational lensing, smudges of red that are actually the first star clusters flickering alive. Some of these galaxies are so far away that they existed only 300 million years after the Big Bang. 300 million sounds like a lot, until you remember the universe is nearly 14 billion years old. In scale, it's like opening a photo album and finding a snapshot from when someone was 3 days old. But Webb's revelations also bring new puzzles. For one, the earliest galaxies appear too grown up. The stars inside them are older and heavier than expected, raising questions about how quickly the universe lit up. Historians still argue whether this means dark matter played a bigger role than we thought, or if star formation physics needs tweaking. Others wonder if Webb might be exposing cracks in our entire cosmological model. Scientists, ever cautious, remind each other not to leap to conclusions. But the whispers are there. Could Webb be hinting at new physics beyond what we know? Here's a humorous tidbit. When Webb released its first images, social media exploded with memes. Some people compared the deep fields to glitter nail polish, others to spilled sprinkles on black frosting. One viral post joked that the universe had turned on 4K resolution. It's classic human behaviour. When confronted with eternity, we reach for dessert metaphors. And maybe that's perfect because these pictures are sweet in a way words can't capture. Still, it's not just about awe. Webb's data is already rewriting textbooks. Its instruments have spotted the chemical signatures of galaxies undergoing furious starbursts, revealed black holes that were already massive at suspiciously early times, and even hinted at exoplanets with surprisingly complex atmospheres. It's like handing a detective a magnifying glass only to find the crimes are messier than anyone imagined. NASA scientists grin through the chaos, knowing this is exactly why Webb was built, not to confirm what we thought we knew, but to break the rules and make us rethink the script. You lean back, closing your eyes, and picture the telescope still out there now, orbiting a million miles from Earth at a spot called L2. It's silent, it's cold, it doesn't care about our earthly dramas. yet it keeps sending home visions that make philosophers, artists, and insomniacs all sit up straighter. If the edge of the universe is a horizon painted in ancient light, Webb is the new set of glasses letting us see the brushstrokes. And perhaps the most humbling part? This is still just the beginning. Webb's mission has years ahead of it, maybe decades. Every month new images arrive, each one a reminder that the cosmos is stranger, richer, and busier than we imagined. The ancient dawn wasn't quiet at all. It was noisy with light, crowded with galaxies, bursting with creation. Webb has simply peeled back the curtains, revealing a stage that was always there, waiting for us to finally look. The golden shimmer of James Webb still glows in your imagination when you suddenly pull back your perspective. You've been gazing at individual galaxies, tiny islands, each its own wonder. But what happens if you zoom out further? What if you look not just at one galaxy or even a cluster, but at the universe itself on the largest scales? What you'd see isn't a random scattering of dots at all. It's a vast architecture, a hidden scaffolding stretching across billions of light years. Astronomers call it the cosmic web, and once you picture it, you'll never see the night sky the same way again. Imagine looking at the universe not in stars or galaxies but in pure matter density, like a 3D map of where stuff clumps together. What you'd see are filaments, long strands of galaxies braided like highways of light, connected at nodes where clusters pile up, leaving behind enormous voids in between. It looks uncannily like a spider's web or, if you're hungry, a bowl of cosmic ramen, with noodles crisscrossing and knots where galaxies swirl together in clusters. Historians still argue whether the phrase cosmic web was coined by journalists for dramatic flair or by scientists themselves, but either way, the metaphor stuck and it fits perfectly. NASA's role in unveiling this structure has been monumental. The Sloan Digital Sky Survey on Earth gave the first hints, mapping galaxies across huge swathes of sky, but it was NASA's telescopes, Hubble, Chandra, Spitzer, that helped probe the details. Then simulations, run on NASA supercomputers, stitched it all together, showing how dark matter, unseen but dominant, forms the skeleton of this web. Galaxies are just the luminous frosting clinging to invisible scaffolding like dewdrops on a spider's thread. Without dark matter pulling the strings, the universe would be a shapeless fog. Here's the quirky tidbit that makes this story extra fun. The large-scale distribution of galaxies, when visualized, looks eerily like neural networks in the human brain. When scientists compared the two structures, billions of galaxies connected by filaments versus billions of neurons connected by synapses, they found statistical similarities. Of course, no one's seriously suggesting the universe is a giant brain-thinking, cosmic thoughts, but the resemblance makes for deliciously trippy conversation. One astrophysicist joked, "Maybe we're just neurons in some larger being's head, and we'll never know until it sneezes." You glide along one of these filaments in your imagination now, galaxies streaming below you like streetlights on an endless highway. The scale boggles you. A single filament can stretch hundreds of millions of light years. A void between filaments can be nearly empty, so vast that if you plop the Milky Way inside, it would feel lonelier than a library at midnight. And yet, step back further, and it all looks connected. An intricate lace of matter, gravity's masterpiece sculpted over billions of years. Historians still argue whether the discovery of the cosmic web was the true turning point in cosmology, more profound even than Hubble's expansion. After all, it didn't just show that the universe grows larger, it showed how it organizes itself, how chaos gives rise to pattern. The idea that something as messy as the Big Bang could eventually weave itself into elegant filaments challenges our instincts about randomness. The web is both structure and story, frozen evidence of how dark matter pulled baryons, ordinary matter, like us, into its invisible blueprint. And NASA doesn't just map it for fun. The web is crucial for understanding dark energy too. By studying how these filaments have grown and stretched over time, astronomers can test how the acceleration of the universe has changed. Roman, Euclid, and other telescopes will measure the wiggles in galaxy clustering called baryon acoustic oscillations, like ripples left over from sound waves in the early universe. Think of it as cosmic echolocation. Galaxies today still remember faint vibrations from billions of years ago, and by measuring those ripples, we learn how dark energy has been whispering in the background all along. But let's lighten the mood with a little humour. If the cosmic web is like ramen, then the voids are the broth. spacious, smooth, and deceptively important. Astronomers even host conferences on voids, with papers titled things like The Physics of Nothing. One researcher once admitted in an interview, "My job is literally to study emptiness." Imagine explaining that at a family dinner. "Oh, you're a doctor. I study nothing." And yet those voids matter. Their size and shape tell us how fast the universe is stretching, and maybe, just maybe, where the new physics is hiding in the gaps. Now, zoom back in. Picture yourself perched on one of the web's intersections where Philome's clements cross. These are galaxy clusters, enormous gravitational knots binding hundreds or even thousands of galaxies. Within them, hot gas glows in X-rays, black holes roar at their centres, and galaxies collide like bumper cars at a carnival. NASA's Chandra X-ray Observatory has imaged these clusters in stunning detail, showing shockwaves, cavities and jets that ripple through space like the echoes of cosmic wars. It's both violent and beautiful, a reminder that the web isn't static but alive with motion. Here's another quirky tidbit. One of the largest structures ever discovered is called the Sloan Great Wall, a colossal chain of galaxies stretching 1.4 billion light-years across. To put that in perspective, if the Milky Way were a single grain of rice, the Great Wall would be a family-sized bag of rice spilling across your kitchen counter. Some scientists debated whether it should even count as a single structure, or if it was just chance alignment. Historians still argue whether these megastructures violate the so-called cosmological principle, the idea that the universe should look roughly the same in every direction. The jury's still out, but the fact that we can even have that debate shows just how big the web really is. You lean back and let the mental picture settle. Galaxies aren't just sprinkled randomly in a void, they're beads on invisible strings woven into a tapestry larger than anything you can grasp. The Milky Way itself is part of a filament, drifting toward the Virgo cluster along gravitational currents we can only measure indirectly. And someday, in the unimaginably distant future, even these filaments may thin out, stretched by dark energy until only local clusters remain bound. But for now, the web holds, shimmering across the cosmos like frost on an infinite window. And maybe, just maybe, there's something comforting in that. You're not a lonely raisin drifting in empty bread dough. You're part of a web, a network, a cosmic structure grander than any cathedral humans have ever built. The same physics that ties galaxies together also ties atoms into molecules, neurons into thoughts. The pattern repeats across scales, whispering that perhaps order is the universe's favourite trick. So as you close your eyes tonight, picture yourself suspended in that web, one luminous node among billions, connected by invisible threads. The edge of the universe isn't just distance, it's structure, pattern and connection stretched across time itself. You're still tangled in the strands of the cosmic web, picturing galaxies strung along filaments, like beads of light, when a subtle tug nudges your imagination. You glance around and notice something odd. The Milky Way, along with thousands of other galaxies in our neighbourhood, seems to be drifting in a particular direction, as though caught in some invisible current. It isn't random motion, it's purposeful, coordinated, a migration across hundreds of millions of light-years. NASA's maps confirm it. We, along with the entire Laniakea supercluster, are being pulled toward a strange gravitational anomaly. Astronomers gave it an appropriately dramatic name, the Great Attractor. Now don't confuse this with a black hole. It's not a single monster swallowing galaxies whole. Instead, it's an enormous region of space thick with mass that exerts a gravitational pull so strong that even galaxy clusters bow toward it. Imagine rafting down a river and noticing that the current, though invisible, keeps dragging you towards some unseen waterfall ahead. That's what the Great Attractor is, a gravitational undertow written into the flow of the cosmic web. The story began in the 1970s and 80s, when astronomers studying galaxy motions noticed something peculiar. Our Milky Way wasn't drifting at random, it was moving at about 600 kilometers per second relative to the cosmic microwave background. Something massive was pulling us. But when telescopes looked in that direction, there was a problem. The view was blocked by the Milky Way itself. Dust, gas and stars along our galactic plane obscured the region, hiding the source. Astronomers nicknamed it the Zone of Avoidance, which, let's be honest, sounds like a level from a video game. Quirky tidbit, some early sky surveys literally left blank spots in their maps there. Not because nothing existed, but because we simply couldn't see through the glare of our own galaxy. Historians still argue whether the discovery of the Great Attractor counts as a true find, or more of a gravitational deduction. After all, we can't photograph it directly like we do a galaxy cluster. What we see instead are the effects, galaxies streaming toward an unseen center, like leaves floating toward a drain in the bathtub. Eventually, deeper infrared surveys began to peer through the dust and revealed something astonishing. The Great Attractor lies near the heart of the Norma cluster, part of an even larger structure called the Shapley supercluster, one of the most massive concentrations of galaxies in the local universe. You try to picture the scale. The Great Attractor isn't a point but a sprawling region hundreds of millions of light years across. Within it are tens of thousands of galaxies, bound together in an enormous knot of the cosmic web. Its total mass is estimated to be more than 100 million billion suns. Numbers like that stop meaning anything after a while, but think of it this way. If the Milky Way were a single speck of dust, the Great Attractor would be a mountain range. And we're sliding toward it, carried along with our neighbours like a convoy of dust motes drifting in a cosmic breeze. Here's the fun, slightly eerie part. We're not falling into the Great Attractor in the sense of doom. The universe's expansion and dark energy keep galaxies from collapsing outright into it. But we are moving relative to the background, inexorably drawn toward its dense heart. Over billions of years, our local group and other clusters may merge with it, knitting into an even grander superstructure. If you thought the cosmic web was already overwhelming, imagine realizing you're inside one of its largest knots, slowly spiraling into an invisible gravitational metropolis. NASA's role in this mystery has been twofold. First, refining the measurements of galaxy motions with satellites like COBE and WMAP, which established our motion relative to the microwave background. Second, partnering with ground-based surveys in infrared to pierce the dust. The more we map, the clearer the picture. The Great Attractor is part of a flow of galaxies streaming not just into Shapley, but along massive filaments that stretch even further. Some astronomers now argue that the true gravitational capital of our region isn't the Great Attractor at all, but the Shapley supercluster farther beyond. Historians still argue whether we should retire the dramatic name or keep it, since honestly, Shapley Attractor just doesn't have the same ring. A quirky human tidbit. When the term Great Attractor first appeared in the 80s, some newspapers ran with headlines like, "Giant cosmic vacuum cleaner sucking up the universe." One tabloid even compared it to a black hole that would swallow Earth within millions of years, which is both wrong and unintentionally hilarious. NASA scientists patiently explained that no, we're not doomed, and yes, we're already moving that way and have been for billions of years. The public, however, briefly imagined being hoovered into some intergalactic drain. It goes to show, give something a dramatic name, and suddenly you've got horror movie material. Let's ground this with an analogy. Imagine living in a small town. You notice that for some reason, all the roads slope ever so slightly in one direction. Cars, people, even rainwater seem to drift that way without trying. Eventually, you realize your town is perched on the slope of a vast valley, and the pull is toward a great city beyond the hills. That city is the Great Attractor, and your town is the Milky Way. We're not being yanked violently, we're coasting downhill, nudged along by gravity's patient hand. And yet, like all cosmic mysteries, the Great Attractor leaves room for speculation. Some astronomers wonder if it hints at even larger structures, beyond Shapley, beyond what we can currently map. There's even talk of a dipole repeller, a region of unusually low density opposite the attractor, as though the universe itself is both pulling and pushing us along. Historians still argue whether these features are real or just artifacts of our incomplete surveys, but the notion adds a touch of balance. The universe doesn't just attract, it repels. Forces push and pull, shaping the grand dance of galaxies. You lean back and imagine the flow, hundreds of thousands of galaxies streaming like schools of fish, guided by invisible currents of gravity. You, tucked away on a quiet spiral arm of the Milky Way, are a passenger on this drift, moving not just through space but toward destiny written in mass. You'll never feel it. Our daily lives aren't disturbed, but the fact remains, every heartbeat you have is happening aboard a galaxy currently migrating toward a hidden congregation of unimaginable scale. And maybe there's comfort in that. You're not drifting alone. Your entire cosmic neighborhood, from Andromeda to Virgo, is in the same current, all being pulled toward the same unseen city in the dark. The Great Attractor isn't a monster to fear. It's a destination, part of the natural flow of the web. If you squint, you can almost imagine it not as a mystery, but as a kind of cosmic hometown, waiting patiently for our arrival. You're still drifting in the current of the Great Attractor, imagining galaxies sliding through invisible rivers of gravity, when your eyes catch something that doesn't fit the serene picture. Out on the horizon, a pinpoint of light blazes so brightly it outshines every star in its host galaxy combined. At first glance, you'd swear it was a star, sharp, piercing, impossible to ignore. But then the scale sets in. This is no ordinary star. This is a quasar, one of the most ferocious lighthouses in the universe, powered not by fire, but by hunger. Quasars are what happen when galaxies feed their central black holes too well. Picture a supermassive black hole millions or even billions of times the mass of the Sun. It sits at the galaxy's core like an insatiable monarch, pulling in gas, dust, stars, anything unlucky enough to wander close. As the material spirals inward, it heats up, colliding and compressing until it glows brighter than the galaxy itself. That glow is what you see, a quasar, a beacon visible across billions of light years. Some of the quasars NASA's telescopes have studied are so far away that their light began its journey when the universe was barely 1 billion years old. The quirky part? The name quasar comes from quasi-stellar radio source. When astronomers first spotted them in the 1950s and 60s, they looked like stars in radio images, tiny pinpricks with no obvious fuzz of galaxies around them. It wasn't until their spectra were analysed that the truth hit. Those stars were actually staggeringly distant, meaning they must be unimaginably luminous. Historians still argue whether the astronomers of the time truly believed their own measurements at first, or if they thought their instruments were broken. Imagine checking your math 3 times and realising, nope, the universe really does contain objects 1,000 times brighter than the Milky Way. NASA, of course, has been obsessed with quasars ever since. The Hubble Space Telescope helped reveal the galaxies that host them, showing distorted structures and evidence of collisions, cosmic feeding events that funneled material into the waiting black holes. Chandra's X-ray vision peered into the hottest, most violent parts of the accretion disks, mapping jets of particles blasting outward at nearly the speed of light. Even the Fermi Gamma Ray Space Telescope got in on the act, detecting high-energy emissions from quasars that make your microwave oven look like a campfire by comparison. You close your eyes and imagine standing near one. The scale is absurd. Around you, a disk of matter swirls at relativistic speeds, glowing hotter than any furnace on Earth. Magnetic fields twist and snap, launching twin jets that shoot for millions of light years into intergalactic space. If Earth orbited near a quasar, our night sky wouldn't just be bright, it would be unlivably radioactive. Thankfully, our galaxy's central black hole, Sagittarius A, is a quiet diner, content to snack lightly rather than gorge. But in the early universe, black holes were less restrained. They feasted, they blazed, they lit up the cosmos with quasar fireworks. Historians still argue whether quasars played a starring role in the universe's reionization, the epoch when the first lights ionized the fog of hydrogen that filled space. Some models suggest quasars' ultraviolet glare helped clear the haze, letting galaxies shine freely. Others argue stars alone did the job, and quasars were just dramatic side effects. The debate continues, but either way, quasars mark an era when black holes weren't passive monsters lurking in shadows. They were cosmic engines shaping the environment around them. Here's a fun tidbit. The most distant quasar discovered so far lies more than 13 billion light-years away. Shining when the universe was just 690 million years old, its black hole is already a staggering 1.6 billion times the mass of the Sun. The problem? Nobody quite knows how such a giant could have formed so quickly. Did it start as a massive seed black hole from collapsing primordial gas clouds? Did it grow by eating at super-Earth speed limits, somehow bypassing the usual rules? Historians still argue whether this means we need new physics or just better models of black hole growth. For now, it's one of those cosmic puzzles Webb and future telescopes will keep poking at. And of course, humans being humans, we can't resist adding a touch of humour to all this grandeur. Some astronomers affectionately call quasars cosmic teenagers, messy, energetic, glowing too brightly for their own good, often the result of collisions between galaxies. One even joked that quasars are black holes on a caffeine bender. It's not wrong. If you want an image that sticks, picture a galactic-sized espresso machine cranked to maximum, spraying jets across intergalactic space. NASA's fascination with quasars isn't just curiosity, it's practical too, because quasars are so bright, They act like flashlights shining through the universe's fog. When their light passes through intervening gas clouds, it picks up absorption lines that tell us what the gas was made of billions of years ago. By analysing these fingerprints, astronomers can reconstruct the chemical evolution of the cosmos, tracing how hydrogen and helium gave way to heavier elements forged in stars. In other words, quasars are both dazzling performers and useful lab tools. Screaming across time while scribbling notes about the medium they pass through, you let yourself drift further into this vision. Imagine looking down on the cosmic web from earlier, but now dotted with quasars like sparks on a vast firework display. They flare and fade, their lifespans relatively short compared to galaxies, tens of millions of years at most, but during that time they alter everything around them. Jets from quasars can blow gas out of galaxies, shutting down star formation. Radiation can sterilize nearby space, while at the same time seeding it with heavy elements. Quasars don't just sit quietly, they remodel their neighborhoods. In that sense, they're both destructive and creative, like cosmic gardeners who prune too aggressively but leave behind fertile soil. Historians still argue whether every galaxy goes through a quasar phase. Some evidence suggests yes, that most large galaxies, including our Milky Way, once hosted an active, ravenous black hole blazing brightly. If so, then quasars aren't just exotic rarities at the edge of the universe. They are a phase in galactic adolescence, a rite of passage on the way to maturity. Today, our black hole is quiet, but who knows? Maybe billions of years ago, the Milky Way was a quasar too, blazing so brightly that if you were watching from afar, you'd have seen us as a quasar dot, unaware of the small blue planet orbiting quietly inside. That thought lingers with you as you relax into the imagery. Out there at the edge of the visible universe, quasars shine like lighthouses, marking not only distance but time. They remind us that hunger is universal, that even in the cosmos, growth comes through appetite, sometimes messy, sometimes violent, always transformative, and though they burn out eventually, their fingerprints remain in the stars around us, in the elements that build planets, and even in the atoms in your own body. So next time you sip your coffee and feel wide awake, remember, somewhere out there a quasar is doing the same thing, only with jets of plasma instead of caffeine. And unlike you, it doesn't need to worry about Monday mornings. You're still watching the quasar blaze, a black hole's hunger lighting up the cosmos like a galactic bonfire, when suddenly the sky delivers something even more extreme, so quick and so violent that if you blink you'll miss it. A flash brighter than anything else in the universe, outshining entire galaxies for a few seconds. This is a gamma ray burst, a cosmic firework so intense it makes quasars look like birthday candles. Gamma rays are the highest energy form of light, invisible to human eyes but lethal in their intensity. When a gamma ray burst, or GRB, goes off, it releases in seconds as much energy as the sun will produce in its entire 10 billion year lifetime. Imagine every light bulb, every steer, every power plant in the observable universe flipping on all at once, and then condensing into a flash you could miss if you happened to be reaching for popcorn. The story of their discovery is quirky enough to belong in a spy novel. Back in the late 1960s, US satellites called the Vela spacecraft were orbiting Earth, secretly watching for gamma rays from nuclear bomb tests. Instead, they picked up strange flashes coming from space. The military declassified the data in the 1970s, and astronomers were baffled. Here were bursts of energy, unpredictable, scattered across the sky. Historians still argue whether the scientists at first truly believed these signals came from the cosmos, or suspected pranksters at Los Alamos were messing with the readings. Either way, the truth was stranger than fiction. The universe itself was detonating fireworks. NASA jumped on the mystery with gusto. Satellites like the Compton Gamma Ray Observatory in the 1990s and the SWIFT mission in the 2000s revealed GRBs in exquisite detail. SWIFT in particular was built like a cosmic paparazzo, able to swivel within seconds to capture bursts as soon as they occur, before they fade. That agility has been crucial because GRBs don't last long. Some flare for just milliseconds, others linger for a couple of minutes, but almost all are gone before you can say, wait, did you see that? So what causes them? There are two main flavours. Long-duration bursts, lasting more than 2 seconds, are thought to come from massive stars collapsing into black holes, their cores imploding while their outer layers blast outward in violent supernovae. Short-duration bursts, less than 2 seconds, likely arise from the collision of neutron stars. Stellar corpses smashing together, shaking space-time itself. Both scenarios are extreme even by cosmic standards. Imagine a pair of city-sized neutron stars, each more massive than the Sun, colliding at a fraction of light speed. The explosion lights up in gamma rays, rattles the universe with gravitational waves, and sprays heavy elements like gold and platinum into space. Yes, the jewellery on your finger probably owes its existence to one of these spectacular collisions. Historians still argue whether every gamma ray burst fits neatly into these two categories. Some seem to blur the line, lasting longer than short bursts but not quite matching supernova signatures. Others show puzzling afterglows that don't fit the models. As with most cosmic mysteries, the more data NASA collects, the more the categories wobble, and the more debates simmer at conferences. But that's part of the thrill. GRBs refuse to be tamed, reminding us that the universe loves variety in its catastrophes. Here's a quirky tidbit. One of the closest gamma ray bursts ever recorded happened in 2008. A burst called GRB 080319b was so bright it could be seen with the naked eye. For about half a minute, if you happened to be staring at the right patch of sky, you'd have witnessed a flash from billions of light years away, visible without a telescope. Astronomers nicknamed it the naked eye burst, and some called it the most violent event humans have ever seen directly. If that doesn't humble you, nothing will. And while we're here, let's sprinkle in some humour. Imagine trying to explain gamma ray bursts to your pet. Yes, Mr. Whiskers, sometimes two dead stars slam together and spray out energy strong enough to vaporise planets. The cat blinks slowly, unimpressed, and goes back to licking its paw. Meanwhile, you're lying awake at night thinking, wait, if one of these happened close to Earth, would we be toast? The answer is yes, kind of. A nearby GRB could strip our atmosphere, wreck the ozone layer, and trigger mass extinctions. Historians still argue whether a past extinction event on Earth was partly caused by a burst. Fortunately, the odds of one going off in our galactic neighbourhood anytime soon are vanishingly small. Still, it's a sobering thought. The cosmos throws fireworks, and sometimes the sparks fly farther than we'd like. But don't let that keep you up tonight. Instead, focus on the wonder of what GRBs tell us. They're not just destructive, they're creative. When neutron stars collide and spray heavy elements into the void, they're literally forging the ingredients of planets, oceans, and people. Your smartphone battery, thank a gamma ray burst for the lithium. Your wedding ring, thank a stellar smash-up for the gold. The universe may use catastrophic events as its alchemy labs, transmuting death into treasure. NASA's Fermi telescope has added another layer of intrigue by detecting gamma rays from bursts at energies far higher than expected. Some lasted not just seconds but hours, with delayed echoes hinting at complex physics in the jets. Are we seeing magnetic fields twist and snap? Or is there something deeper, new particles, exotic physics beyond the standard model hiding in the glow? Historians still argue whether these anomalies are hints of breakthrough discoveries or just the quirks of messy astrophysical explosions. You let yourself drift into the imagery. A dark, silent universe suddenly pierced by a flash so bright it briefly rewrites the sky. The afterglow fades in X-rays, then in visible light, then in radio waves like ripples spreading across a pond. Instruments on Earth scramble to catch the fading signal, while satellites record every photon. Somewhere in a control room, scientists cheer because catching a gamma ray burst feels like spotting a shooting star that not only grants a wish, but also explains how half the elements in your body got here. And just when you think the universe can't get weirder, gamma ray bursts intersect with another frontier: gravitational waves. In 2017, detectors on Earth picked up ripples in spacetime from two neutron stars colliding. Almost immediately, satellites detected a gamma ray burst from the same event. It was the first time we'd ever caught both light and gravitational waves from the same source, a cosmic duet that confirmed decades of theory. Historians still argue whether that day marked the birth of multi-messenger astronomy, or if earlier hints deserve the title, but either way, it was a watershed moment. Suddenly we weren't just looking at the universe, we were listening to it too. You smile as you imagine it, cosmic fireworks exploding in gamma rays, shaking, space-time like a drum, sprinkling gold dust into the void. Violent? Absolutely. Terrifying? Maybe. But also strangely beautiful. The universe doesn't just whisper in microwaves or drift in webs, it occasionally shouts, "Watch this," and lights up the sky with a brilliance beyond comprehension. So the next time you see fireworks on Earth, crackling across the 4th of July sky or sparkling on New Year's Eve, remember, those little pops and bangs are humble echoes of a much grander tradition. Out at the edge of the universe, the cosmos has been throwing fireworks for billions of years, each one brighter than galaxies, each one leaving behind the ingredients for life itself. You're still blinking from the afterimage of a gamma ray burst, the sky briefly rewritten by an explosion brighter than a billion galaxies, when a quieter thought sidles in. If the universe can throw fireworks like that, if it can expand, accelerate, weave itself into webs, and whisper with ancient afterglows, then maybe the real shock isn't what NASA has already found. Maybe it's what lies just out of reach. What if our universe is only one chapter in a bigger library? What if the cosmic edge we're straining to see is just the wallpaper of a multiverse? The idea isn't new. Philosophers and mystics toyed with multiple worlds for centuries. But in modern science, the conversation really picked up in the late 20th century, when cosmologists tried to understand why the universe looks the way it does. Our laws of physics, our constants, the fact that stars and planets can even exist, it all feels strangely tuned, balanced between chaos and nothingness. Historians still argue whether this fine-tuning is an illusion or a clue. Enter the multiverse. Maybe our universe is just one bubble among countless others, each with its own physics. We happen to live in the bubble where the constants allow pizza, kittens, and YouTube videos. NASA, of course, doesn't officially put multiverse exploration on its mission statements. They're grounded in what instruments can measure. But here's the quirky part. Anomalies in the data occasionally tease at something beyond. For example, that mysterious cold spot in the cosmic microwave background we mentioned earlier. Some scientists suggested it could be the scar of our universe brushing against another bubble. Imagine two soap bubbles colliding in the sink. Their skins distort, leaving imprints. Could the cold spot be such an imprint? Historians still argue whether it's just a statistical fluke or something deeper, but the fact the question is even asked shows how far our imagination has stretched. Let's pause for humour before this gets too heavy. Picture yourself walking into NASA headquarters and suggesting with a straight face that their next telescope should look for alternate universes. Someone might raise an eyebrow, sip their coffee, and mutter, "Sure, right after we finish mapping this one." The truth is, detecting other universes is tricky, kind of like trying to spy on your neighbour's house while trapped inside your own with the blinds drawn. Still, scientists can't resist poking the idea. Some theories of inflation, the rapid expansion thought to have happened fractions of a second after the Big Bang, naturally lead to a multiverse. In those models, inflation doesn't stop everywhere at once. Instead, some regions stop expanding while others keep going, endlessly bubbling new universes into existence. That picture is called eternal inflation, and it implies an infinite quilt of universes, each with its own initial conditions. NASA doesn't measure this directly, but every map of the microwave background, every probe of cosmic structure, every test of inflation indirectly feeds the debate. And then there's string theory. In its attempt to unify physics, it predicts a vast landscape of possible universes, each corresponding to a different way the extra dimensions of space could be curled up. It's a little like opening a cosmic IKEA catalogue and realising there are more universes than you could ever assemble, even with the right Allen wrench. Historians still argue whether string theory is science or philosophy in disguise, but its influence keeps the multiverse alive as a serious possibility. Here's a quirky tidbit for you. Some scientists have even tried to test the multiverse idea through computer simulations, looking for what they call bubble collision signatures in the microwave background. None have been confirmed, but the very effort shows the lengths to which curiosity can drive us. Imagine spending years searching data for faint circles in a map of the sky, all in the hope that one might be the fingerprint of another universe brushing against ours. If that isn't scientific devotion, I don't know what is. Of course, the multiverse has critics. Some argue it isn't testable and therefore doesn't belong in science. After all, how do you observe a universe you can't enter? Others counter that even if we can't see other universes directly, we can infer their existence from patterns in our own. Historians still argue whether science should stick strictly to what's observable, or if it should allow reasoned extrapolations when the math points that way. For now, the multiverse sits in that twilight zone between physics and philosophy, tantalizing and frustrating in equal measure. You lean back in your chair and let your imagination roam. Picture an infinite froth of universes, each bubbling into existence with its own laws. In one, gravity might be twice as strong, crushing stars before they can shine. In another, chemistry might never allow life. In yet another, perhaps life thrives in forms we can't imagine. And somewhere, maybe, there's a universe just like ours but slightly different, where you're listening to this story in a parallel timeline, perhaps wearing socks of a different colour. A bit of humour. Physicists sometimes joke about the many worlds interpretation of quantum mechanics, where every quantum decision spawns a new universe. In that view, there's a version of you who decided not to listen to this at all, another who fell asleep halfway, and another who's already commented below saying, first, the joke lands because it highlights both the absurdity and the allure of multiverse thinking. It stretches the boundaries of what we consider real. NASA's telescopes, whether they mean to or not, occasionally brush against the edges of this speculation. The James Webb Space Telescope, for instance, has already revealed galaxies that seem too massive too early. Could it be that our physics is missing something fundamental, something that might even point to deeper realities? Nobody knows, but the whispers are enough to fuel countless debates over coffee at conferences, where scientists sketch wild ideas on napkins while admitting they might never know for sure. And yet, there's something strangely comforting in the multiverse idea. If true, it means our universe isn't alone. We're part of a vast ensemble, a cosmic orchestra where each universe plays its own tune. We may never hear the others, but knowing they might be there reframes our loneliness. It makes our bubble less fragile, our existence less improbable. Historians still argue whether the multiverse makes humanity feel smaller or larger, but perhaps it does both. Smaller in scope, larger in possibility. As you drift further into the thought, you realize that the multiverse, whether real or not, has already done its job. It pushes us to think beyond edges, beyond horizons, beyond the comfort of a single story. NASA might not yet find evidence of other universes, but in chasing the possibility, it sharpens our understanding of our own. And in the quiet of the night, when the gamma-ray fireworks have faded and the cosmic web stretches overhead, it's enough to know that the mystery remains open, daring us to keep imagining. So the next time someone asks what NASA found at the edge of the universe, you can smile and say, maybe not just galaxies, not just quasars or dark energy, but the hint that our universe itself might be one bubble in a sea of infinity. You let the thought of infinite universes simmer in the back of your mind, bubbles frothing in a cosmic sink, when NASA tugs you gently back to this universe, the one we can actually measure, map and photograph. Because even if there are countless others, this one still has edges worth chasing. And one of the most exciting quests has been the search for the farthest galaxy ever found. A fragile smudge of light at the limits of what telescopes can see. A postcard mailed from the dawn of time. Imagine the challenge. You're trying to catch the faintest glimmers of light stretched to near invisibility by billions of years of expansion. It's like trying to read the glow of a single candle on a mountaintop, while standing on another mountain hundreds of miles away, with a fog machine and sunglasses thrown in for good measure. Yet NASA and its partners keep pushing, squinting into the darkness until those smudges resolve into galaxies. One of the record breakers, announced in late 22, is a galaxy with the unromantic name Glass Z13. It was spotted by the James Webb Space Telescope during its very first deep surveys. The Z13 refers to its redshift, basically how stretched its light is, with higher numbers meaning greater distance and older age. At Z13, this galaxy is seen as it was just 300 million years after the Big Bang. Think about that. The universe was barely 2% of its current age when this little collection of stars was already shining. Historians still argue whether Webb's candidates like Glass Z13 and its neighbours are truly that far, or if further analysis will shift them slightly closer. But either way, they're among the oldest galaxies ever glimpsed. You lean in closer, picturing what Glass Z13 might actually look like if you could hover nearby. Spoiler, it's not some grand spiral like the Milky Way. At that early time, galaxies were tiny, irregular, more like cosmic building blocks than finished cathedrals. Imagine a few 100 million stars clumped together, glowing faintly red from distance and youth, struggling against gravity to hold their shape. Yet even in their awkward infancy these galaxies were already laying the foundations for the grand structures that would follow, filaments, clusters and superclusters threading across the cosmos. Here's a quirky tidbit. When astronomers announce discoveries like Glass Z13, they almost always include a disclaimer: pending spectroscopic confirmation. Why? Because measuring distance from colour alone, photometric redshift, can be tricky. Dust and other effects can mimic high redshift. Only by splitting the light into a spectrum can you be sure. So in a way, every record-breaking farthest galaxy comes with a little asterisk. Historians still argue whether the public announcements are premature hype or necessary sparks to inspire wonder. Either way, NASA knows how to capture attention, show the faint red smudge, tell us it's older than Earth itself, and let our imaginations do the rest. And speaking of Earth, remember this: when light from Glass Z13 began its journey, Earth didn't exist, the Sun didn't exist. The Milky Way as we know it wasn't even fully formed. That light has been running for over 13 billion years, dodging expansion, stretching thinner and redder with every passing eon, until it finally landed in Webb's gold-plated mirror. You and I are among the first beings to witness it. That's not just science, that's poetry disguised as data. NASA's earlier champion was GNZ11, discovered with Hubble in 2016. It was at redshift Z11, about 400 million years after the Big Bang. For years, it held the crown as the most distant confirmed galaxy. GNZ11 is tiny compared to the Milky Way, maybe 100th its size, but it's blazing with star formation, churning out new suns at a furious pace. Think of it as a toddler sprinting before it's even learned to walk. Historians still argue whether galaxies like GNZ are anomalies or evidence that cosmic structures grew faster than models predict. But with Webb's discoveries, GNZ11 has become the elder sibling in a growing family of early galaxies. Let's sprinkle in a little humour. Scientists often give galaxies designations that sound like Wi-Fi passwords: Glass 13, GNZ11, EGS7. One astronomer joked, "We should start naming them after breakfast cereals. At least people would remember." Imagine reading headlines like "Farthest Galaxy Discovered Frosted Flakes 27. But in truth, the dry names reflect the seriousness of the data. They're catalogue entries, coordinates in the Great Library of the Sky. Still, you can't help but imagine little Glass Z13 introducing itself shyly at a galactic reunion. "Hi, I'm Z13, nice to meet you. Please don't ask me to spell it." What makes these discoveries so profound isn't just the numbers, it's what they imply. If galaxies existed this early, then stars had to form even earlier. That means the first generation of stars, so-called population 3 stars, made purely of hydrogen and helium, may have ignited only 100 million years after the Big Bang. These stars, massive and short-lived, would have seeded the universe with heavier elements when they exploded. Without them, there would be no carbon for life, no oxygen for breath, no iron for blood. So when NASA announces a faint red smudge, what they're really showing us is the cradle of everything we know. Historians still argue whether Webb has already glimpsed population 3 stars indirectly. Some spectra show unusual signatures, perhaps the fingerprints of metal-free stars, but confirmation remains elusive. If Webb or its successors ever find clear evidence, it would be one of the holy grails of astronomy, seeing the very first starlight, the universe's first attempt at illumination. Until then, the farthest galaxies act as lighthouses, pointing us toward that dawn. And here's another quirky detail. Gravitational lensing often helps in the hunt. Massive galaxy clusters can act like magnifying glasses, bending and amplifying the light of galaxies behind them. Some of the farthest candidates NASA has spotted were boosted this way, their light warped into arcs and smears by the gravity of intervening clusters. It's a cosmic cheat code using nature's own telescope to extend ours. Without lensing, many of these galaxies would be invisible. With it, they shine just enough to be caught. Imagine yourself standing on one of those distant galaxies, looking back at the young universe around you. The sky would be crowded with other proto-galaxies, glowing faintly, while great clouds of hydrogen gas still filled the void. Stars would flare and die in quick succession, black holes would be busy at work, and the whole scene would be more chaotic than the relatively settled cosmos we know now. It wouldn't feel like a quiet night. It would feel like a construction site, sparks flying everywhere as the universe built itself in real time. And perhaps that's the most humbling thing about the farthest galaxies. They remind us that we're latecomers. By the time Earth formed, The universe was already more than 9 billion years old. By the time humans appeared, galaxies had been evolving for eons. Yet somehow, with our fragile eyes and fragile machines, we've managed to catch the faint light from those earliest days. Historians still argue whether we should call these galaxies firsts when surely others existed even earlier, invisible to us for now. But that's the beauty. Every record is temporary, every boundary meant to be broken. You lean back, letting the image of glass Z13 settle in your mind. Just a smear of red pixels, yet heavy with meaning. A galaxy so far, so faint, so early that its light almost didn't make it. And yet it did. It crossed billions of years, survived the stretching of space and landed in a telescope orbiting a small Biba, rocky planet whose inhabitants built machines to wonder at the sky. That improbable chain of events leads right here to you listening to this story. So when NASA says they've found the farthest galaxy, remember, it's not just a record for the books. It's a message from the dawn, proof that the universe wastes no time in making wonders, and that curiosity, yours, mine, humanity's, is strong enough to catch even the faintest whispers across eternity. You're still holding that faint red smudge of a galaxy in your mind, marveling at how NASA managed to catch light from the universe's earliest dawn when you realize a secret. We didn't find it alone. The universe itself lent us a hand. Out there in the dark, massive clusters of galaxies bent space like funhouse mirrors, warping light and magnifying distant objects behind them. These are gravitational lenses, and they've turned out to be some of the most powerful magnifying glasses we'll ever have. The idea traces back to Albert Einstein, who in 1915 showed that gravity isn't a force pulling through space, it is space, bent and curved by mass. If you drop a bowling ball on a trampoline, the fabric sags, and marbles rolling nearby spiral toward it. Light, being obedient to geometry, also follows those curves. So when light from a distant galaxy passes near a massive cluster, it bends, arcs, sometimes even splitting into multiple images. To the astronomer, it looks like nature itself built a telescope boosting faint galaxies into visibility. Historians still argue whether Einstein ever thought his prediction would be observable. He once called the effect of little practical significance. A century later, it's one of the hottest tools in cosmology. Picture yourself drifting through space, approaching a galaxy cluster the size of millions of Milky Ways glued together. Around it, arcs of light shimmer, stretched images of background galaxies, distorted like reflections in a wine glass. Some form complete rings, called Einstein rings, glowing halos that look almost like neon signs advertising the secrets of the cosmos. Others appear as streaks and smears, but behind the distortion lies truth, galaxies so distant and faint we'd never have seen them without the lens. NASA's Hubble Space Telescope has been the master of this trick. Its images of gravitationally lensed galaxies are some of the most surreal ever taken. The Hubble Frontier Fields program, launched in the 2010s, deliberately pointed at massive clusters to exploit their magnifying power. The result? Some of the deepest views of the universe ever achieved, revealing galaxies from less than 1 billion years after the Big Bang. It was like sneaking a peek through a cosmic peephole into the nursery of creation. Here's a quirky tidbit. One of the most famous lensed galaxies is nicknamed the Cosmic Horseshoe because the bending of light created a near-perfect arc around a massive galaxy. Another, the Cosmic Eyebrow, looks like, well, a raised eyebrow arcing across the sky. Astronomers, despite their serious math, can't resist playful nicknames. Imagine a NASA press release with phrases like, "Horseshoe confirms early galaxy star formation." It sounds like a pony did the science. The technique isn't just pretty, it's powerful. Gravitational lenses don't just magnify, they also let scientists map the distribution of dark matter. Because dark matter makes up most of a cluster's mass, the way it bends light reveals its otherwise invisible presence. By tracing arcs and rings, NASA has drawn maps of dark matter halos, showing how it clumps around galaxies like an invisible spiderweb. Historians still argue whether these maps perfectly align with our models or hint at new physics, but either way, they prove dark matter is more than theory. It leaves fingerprints in bent light. You imagine floating along one of those arcs now, surfing the stretched light of a galaxy behind the lens. That galaxy's photons have been travelling for over 13 billion years, only to encounter a massive cluster that nudged them just enough to aim into Hubble or Webb's mirror. Without that nudge, they'd have missed us completely. It feels almost conspiratorial, as if the universe itself wants us to see its secrets, bending light into our view like a magician sliding a hidden card into your hand. Of course, gravitational lensing can also play tricks. Sometimes the same background galaxy appears multiple times in the same image, split into mirror images. Astronomers have spotted instances where one galaxy shows up as 3 separate arcs, like identical twins photobombing each other. This duplication can be more than amusing. It lets scientists measure cosmic expansion by comparing the arrival times of light. Historians still argue whether the precision of these time delay measurements can solve the current tension over the Hubble constant, but it's one of the cleverest experiments out there. Here's another quirky detail. Gravitational lensing has been used to detect planets in other galaxies, something otherwise impossible. By observing tiny, brief distortions in light from lensed quasars, astronomers have inferred the presence of planet-sized masses in galaxies millions of light-years away. Think about that. We can't see those planets directly, but we know they're there because their gravity ever so slightly tweaked a photon's path across unimaginable distance. It's cosmic detective work of the highest order. NASA's upcoming Nancy Grace Roman Space Telescope will take this even further. Its wide field of view will allow it to capture thousands of lensed galaxies, creating a statistical goldmine for studying dark energy, galaxy evolution, and cosmic structure. Imagine opening a scrapbook filled not with selfies but with distorted mirror images of the universe itself, each one whispering, "Here's what gravity can do when it really shows off." Humour break, some astronomers like to call gravitational lensing cosmic Photoshop. After all, the universe is literally stretching and warping the shapes of galaxies before they hit our cameras. Only difference, these distortions are real, not retouched. Somewhere a galaxy billions of light-years away might actually be round and elegant, but to us, it shows up looking like a smear of toothpaste across the cosmic canvas. Nature, apparently, has a sense of humour about optics. And yet, for all the odd shapes, lensing gives us one of the most intimate connections with the early universe. Those faint, magnified galaxies behind the clusters aren't just records of early star formation, they're snapshots of how the first cosmic structures took root. They help scientists test when and how the cosmic dawn transitioned into the era of galaxies we see today. Without lensing, many of these galaxies would be invisible, their photons lost forever. With it, we get VIP tickets to the first light show ever staged. Historians still argue whether gravitational lensing will ultimately solve the dark matter puzzle. Some lensing maps show clumps of dark matter not quite where models predict, raising whispers of new physics. Others line up perfectly, reinforcing the standard picture. The debates rage on, but lensing remains the best evidence we have of the invisible. Matter we cannot see, shaping the paths of photons we can. It's the universe reminding us that not all truth is visible, but all truth leaves a trail. As you let this thought settle, you imagine the universe as a hall of mirrors. Light bends, stretches, duplicates, hides and reveals. NASA's telescopes are like guests wandering through, snapping photos of reflections that at first seem distorted, but, upon study, reveal more than straight views ever could. The edge of the universe isn't just out there, it's bent around corners, hidden behind clusters, magnified by the geometry of space itself. So the next time you hold up a magnifying glass to read a tiny label, think of this. The universe has been doing the same trick on a grander scale for billions of years, bending ancient starlight just enough to let us glimpse the unreachable. And thanks to NASA, we've learned how to read those warped messages, transforming distortions into discoveries. You're still gazing at those warped arcs of light bent by gravitational lenses, marvelling at how the universe itself sometimes hands us magnifying glasses when the picture fades to black. Imagine rewinding the cosmic clock further back past the farthest galaxies, past the first lighthouses of stars, to a time when the cosmos had no light at all. No galaxies, no quasars, no fireworks, just darkness, vast and heavy. This was the cosmic dark ages, a stretch of time after the Big Bang when the universe existed, but looked utterly blank. It's not the kind of darkness you know from switching off your bedroom lamp. This was a deeper void, a universe filled with hydrogen and helium gas, still cooling from the Big Bang but with no stars to ignite. Imagine standing on a shore before the first sunrise in history. The ocean is there, the air is there, but the sky is nothing but ink. The cosmic dark ages lasted hundreds of millions of years, a silent interval before creation's first sparks. The story begins around 380,000 years after the Big Bang. Before that, the universe was a dense plasma, so hot that photons couldn't travel freely. It was like trying to see through boiling soup. Light was constantly scattered. But as the universe expanded and cooled, protons and electrons combined into neutral atoms, letting light travel at last. That relic light became the cosmic microwave background, the baby picture we talked about earlier. After that release, though, everything went quiet. Photons streamed freely, but there were no stars to shine, no galaxies to glow. Just neutral hydrogen filling an ever-expanding void. Historians still argue how long exactly the Dark Ages lasted. Estimates suggest maybe 100 million years before the first stars flickered, maybe a bit longer. But in cosmic terms, it was a pause, a long night between the heat of the Big Bang and the light of the first dawn. NASA's telescopes can't see into this era directly with visible light. It's too blank. Instead, they hunt for indirect traces, like archaeologists looking not for pottery but for soil layers that whisper of things buried below. Here's a quirky tidbit. Astronomers sometimes joke that the cosmic dark ages were boring, but only in the sense that nothing visible was happening. In reality, this was when matter was quietly assembling into the seeds of galaxies. Dark matter clumped first, invisible halos forming gravitational wells. Hydrogen gas began to fall into these wells, cooling and condensing. The stage was being set. It's like calling pregnancy boring because you can't see the baby yet. Something extraordinary was brewing, invisible but inevitable. NASA's James Webb Space Telescope is now probing galaxies so young they practically touch the end of the Dark Ages. Its deep field images capture galaxies from only 300 million years after the Big Bang, hinting at the tail end of the darkness. But the true Dark Ages, earlier than Webb can reach, remain one of astronomy's great frontiers. Future missions, like the proposed hydrogen mapping telescopes, aim to detect faint radio signals from neutral hydrogen itself. The quiet background song of a universe still waiting for its lights to turn on. Let's lighten the mood with a little humour. Imagine trying to pitch the Dark Ages as a tourist attraction. Come visit the early universe. No stars, no galaxies, just endless hydrogen. Not the most compelling brochure, and yet, from a scientific standpoint, it's one of the most intriguing eras, because it was the blank canvas on which everything else was painted. Without understanding the Dark Ages, you can't fully appreciate the brilliance of the first dawn. Historians still argue whether the first stars formed in small clumps or larger bursts. Some models suggest tiny protogalaxies with just a few hundred stars. Others hint at bigger, more dramatic collapses, forming clusters right away. Either way, those first stars, called population 3 stars, were unlike anything alive today. Massive, hot, short-lived, and made of pure hydrogen and helium, they were the universe's first attempt at alchemy. Their deaths seeded the cosmos with heavier elements, carbon, oxygen, iron, that later generations of stars would inherit. Without them, there would be no rocky planets, no oceans, no biology. The Dark Ages were the prelude to everything you know. NASA scientists sometimes describe this era as the universe's teenage years, awkward and transitional, full of invisible growth spurts. You can't see the changes directly, but you know they're happening. Galaxies were forming in secret, black holes preparing their first meals, matter settling into the patterns that would later become the cosmic web. The silence was deceptive. Beneath it, the machinery of creation was already humming. Here's another quirky tidbit. The term Dark Ages itself was borrowed from human history, where it referred to periods of cultural decline or missing records. Some historians of science argue the label is misleading because while the universe was visually dark, it wasn't inactive. In fact, it was crucial. Calling it dark risks underselling it. Still, the phrase stuck, partly because the cosmic quiet pre-dawn interval doesn't quite have the same drama. Imagine yourself floating through this era. There are no constellations, no Milky Way arc overhead. Instead, the sky is uniform, glowing faintly with the fading warmth of the microwave background. Around you, clouds of hydrogen stretch endlessly, smooth and undisturbed, like a fog with no horizon. Then slowly, imperceptibly, ripples form. Tiny overdensities seeded by quantum fluctuations from the Big Bang. Gravity gathers these ripples, deepening them, pulling in more matter. You can almost feel the tension building, like the silence before a concert when the instruments are tuned, but the first note hasn't played. NASA's future plans include hunting for the faint 21-centimeter radio line from hydrogen atoms in this era. If we can map that signal, we'd literally watch the Dark Ages unfold, seeing the moment when the fog thickened and then slowly began to lift as stars turned on. It would be like turning on night vision goggles and suddenly spotting the outlines of a forest in what looked like empty blackness. Historians still argue whether upcoming telescopes will achieve this cleanly, or if interference from Earth will make it maddeningly difficult. But the prize is too tempting to ignore, and maybe that's why the Dark Ages capture imagination despite their apparent emptiness. They remind us that silence isn't absence, it's potential. The universe wasn't idle, it was preparing. Every galaxy, every quasar, every burst of light we've talked about so far had its roots in this unseen epoch. It's the longest inhale before the exhale of starlight. So, as you let your mind drift tonight, picture yourself lying back in that primordial darkness. Feel the stillness, the quiet, the weight of a cosmos waiting to awaken. It's eerie, yes, but also calming, because you know what comes next, the first sparks, the breaking of the silence, the dawn of stars that will end the darkness forever. You're still floating in that eerie silence of the cosmic dark ages, wrapped in endless hydrogen fog, when finally it happens. A spark, then another, then thousands. The black veil begins to tear, replaced by the first fragile glimmers of starlight. This is the era astronomers call cosmic ray ionization, the time when the first stars and galaxies ignited and transformed the universe forever. It was the breaking of the silence, the cosmic dawn. Here's the setup. After the Big Bang, the universe cooled into a sea of neutral hydrogen. Light couldn't travel far through that fog. It was absorbed, scattered, hidden. But when the first stars lit up, their ultraviolet radiation was fierce enough to rip electrons away from hydrogen atoms, ionizing them. Suddenly the fog began to clear. For the first time since the Big Bang, light could sweep freely across space. The Dark Ages ended, and the universe stepped out of its shadow. NASA scientists love to describe this moment as the universe turning the lights on. Historians still argue over exactly when it happened. Estimates suggest ionization began around 400 million years after the Big Bang and wrapped up by about 1 billion years. But the details remain hazy, like trying to reconstruct sunrise from second-hand reports. Webb, Hubble, and other telescopes are piecing together the story galaxy by galaxy, photon by photon. The stars responsible weren't like the ones you see in tonight's sky. These were the so-called population 3 stars, giants tens or even hundreds of times the mass of the Sun, burning ferociously hot, living only a few million years before collapsing into black holes or exploding as supernovae. They were messy, unstable but brilliant. Their radiation shredded the hydrogen fog, carving bubbles of ionized space around them. Over time, these bubbles grew and merged until the entire cosmos was cleared. Imagine looking down on a forest at night, each tree lighting a campfire. At first, the glow is patchy, scattered. Then the flame spread, and soon the whole forest blazes with light. Here's a quirky tidbit. Detecting reionization isn't like catching a single event. It's more like reading graffiti on ancient walls. Astronomers look for the fingerprints of hydrogen gas in the light from distant quasars and galaxies. Quasars are especially useful because their bright light passes through vast stretches of hydrogen. If the light shows gaps, regions where hydrogen blocked it, we know reionization wasn't complete yet. These gaps, called Gunn-Peterson troughs, are like ancient roadblocks in the cosmic highway. They tell us exactly how foggy the early universe was. NASA's telescopes, particularly Hubble and Webb, have been crucial here. Hubble's deep surveys spotted galaxies at redshifts of 6 to 10, prime reionization territory. Webb has pushed even further, finding galaxies at redshifts 12 and beyond. Historians still argue whether Webb's early results suggest stars formed faster than expected, but the excitement is palpable. We're finally peeking into the very transition when the universe lit up. Humor break. Some astronomers casually call this epoch cosmic dawn, which makes it sound poetic and peaceful, but really it was chaos. Giant stars were exploding left and right. Black holes were slurping gas like milkshakes, galaxies were colliding and merging. The dawn was less a gentle sunrise and more like turning on every stadium floodlight at once while setting off fireworks and tossing in a few hurricanes for good measure. If you could somehow vacation there, you'd need radiation shielding, noise-cancelling headphones and nerves of steel. And yet, out of that chaos came clarity. Rayonization made the universe transparent. It allowed light to travel freely, paving the way for the galaxies and structures we see today. Without it, the cosmos would still be shrouded, invisible. It's one of those paradoxes. Destruction, ripping electrons from the atoms, was necessary for creation, for openness, for vision. Historians still argue who the main culprits were. Were the first stars the primary drivers? Or were galaxies, with their collective populations of smaller stars, more important? Or did quasars, those hungry black holes, provide the extra radiation needed to finish the job? Different studies point in different directions. Perhaps it was teamwork, stars starting the work, galaxies sustaining it, quasars giving the final push. The debate continues and NASA's instruments are right in the thick of it. Here's another quirky tidbit. The 21-centimeter hydrogen line, the faint radio signal emitted by neutral hydrogen, is one of the holy grails of rayonization research. By mapping how that signal disappears over time, astronomers could watch the fog lift in 3D. Several projects, including NASA collaborations, are working on it, but Earth's own radio chatter makes it tricky. Imagine trying to hear a whisper from across a crowded stadium. Still, if scientists succeed, they'll have a front-row seat to the cosmic dawn, seeing the fog clear frame by frame. You picture it now, bubbles of ionized gas growing like holes in Swiss cheese, expanding, merging, until the cheese is gone and only the light remains. That's the universe during rayonization, a patchwork of darkness and brightness, transition and transformation. The edge of the universe in this case isn't distance, it's visibility. It's the difference between a fogged-up window and one suddenly wiped clean. And maybe there's something poetic in the timing. The Dark Ages lasted hundreds of millions of years, longer than the time between the extinction of the dinosaurs and today. Yet once light began, it spread quickly, sweeping across the cosmos in less than 1 billion years. It's as though the universe, patient and quiet, suddenly couldn't wait any longer. The silence ended, and the flood of light rushed out in a hurry. NASA scientists sometimes compare it to a cosmic adolescence. The universe went from silent, invisible potential to noisy, luminous chaos. It was messy, awkward, but necessary. Without it, galaxies like ours could never have formed. Stars wouldn't have spread heavy elements into space, planets, life, and you wouldn't exist. Rayonization is the bridge from blank canvas to masterpiece. So as you sit back and picture it, let yourself feel the drama. The first sparks breaking the silence, the fog tearing apart, the light spreading like wildfire. Imagine standing there at the dawn, surrounded by giant stars flaring to life, their light cutting through the mist, announcing, the universe is awake. And maybe that's the lesson for tonight. The darkness never lasts forever. Even in the coldest silence, the seeds of light are waiting. And when they arrive, they don't just illuminate, they transform. You've just watched the cosmic dawn unfold in your imagination. The fog torn apart, the first stars igniting, galaxies glowing for the first time. And then the question that keeps NASA awake at night creeps in. When we say the edge of the universe, what do we really mean? Is there a border out there, a cosmic wall we could someday bump into? Or is it more subtle, more slippery? A horizon beyond which we simply can't see? The difference between an edge and a horizon might sound like semantics, but in cosmology, it's everything. First, let's tackle the human instinct. We're wired to think of edges as boundaries, cliffs, fences, walls, the lip of a plate where spaghetti stops and tablecloth begins. So naturally, when you hear the edge of the universe, you imagine some colossal wall of stars or a cosmic void where existence simply ends. But that isn't how it works. The universe doesn't have an edge in the traditional sense. It's not a snow globe floating in a bigger room. Instead, it's more like standing on Earth and asking, where's the edge of the planet? There isn't one. You just keep going in circles. Here's the quirky tidbit. Some early thinkers really did imagine a literal edge. In the Middle Ages, people debated whether the stars were set into a crystalline sphere surrounding Earth. Even after telescopes shattered that idea, edge thinking persisted. Historians still argue whether even Edwin Hubble, upon discovering expansion, thought of it as galaxies rushing into pre-existing space, Or if you fully grasp the subtler truth, space itself was stretching. Today, cosmologists make a point of saying the universe isn't expanding into anything, it's just expanding, which is about as satisfying to the human brain as being told the cookie jar is infinite but also empty. What we actually face isn't an edge but a horizon. Light travels at a finite speed, and the universe has a finite age, about 13.8 billion years. That means there's only so much of the cosmos we can see, defined by how far light has had time to reach us. This sphere is called the observable universe, and its radius is roughly 46 billion light-years in every direction. Notice that number is bigger than 13.8. That's because space itself has been expanding the whole time. So the galaxies that emitted the first light we're now catching have since moved farther away. Imagine watching a ship's lantern from across the ocean. By the time the light reaches you, the ship itself is already miles farther out. So when NASA says it's peering to the edge of the universe, they really mean the edge of the observable part. Beyond that, more universe exists, but we can't see it. Its light simply hasn't had time to arrive. It's not that the universe ends there, it's that our vision does. Like standing in a foggy field with a flashlight but you can only see as far as the beam reaches. Historians still argue whether we should even use the word edge, since it misleads the public into picturing a literal wall. Some prefer cosmic horizon. Either way, it's a boundary not of space but of time. You lean back and let that thought settle. Imagine yourself standing on a balcony overlooking an endless plain. The horizon stretches away in every direction. You know the land continues past it, but you'll never see farther. Curvature hides it. That's the universe. There is more beyond what we see, perhaps infinitely more, but our horizon limits us. NASA's telescopes are like binoculars. They can sharpen the view, but they can't extend it past the curve. Here's where it gets even stranger. The horizon isn't fixed. Over cosmic time, it changes. In the early universe, the horizon was much smaller. Galaxies that are visible today were once beyond it. As time goes on, more light has time to reach us, so our horizon grows. But dark energy complicates things. Because expansion is accelerating, galaxies are slipping away faster than their light can ever catch up. That means some parts of the universe are already permanently beyond reach, no matter how long we wait. It's like chasing a receding train. You can see its light for a while, but eventually it outruns you forever. Historians still argue whether this realization should be called tragic or simply humbling. On one hand, it means there are wonders we'll never glimpse, not even in principle. On the other, it means the observable universe is a unique window, one we're lucky to catch while it's still so rich with galaxies. Far in the future, if dark energy keeps up, distant galaxies will vanish from view, leaving only the local group. Future astronomers might look out and see nothing beyond their galactic neighborhood, never suspecting the cosmos was once full. In a sense, we live at a privileged time, when the horizon is wide and the story is still visible. Quirky detail, the word horizon comes from the Greek horizon kyklos, meaning limiting circle. And that's exactly what it is in cosmology. The circle beyond which we can't know, but unlike an earthly horizon which you can walk past, the cosmic one is absolute. You can never reach it because it's not a location, it's a limit set by light and time. Let's throw in a little humour. Imagine explaining this at a dinner party. The universe has no edge, only a horizon. Someone squints and asks, "So, if I keep flying in a straight line, what happens?" You sigh and take another sip of wine. You'd never hit a wall, you'd just keep going, forever, while more universe unfolded around you. Cue the awkward silence, followed by someone changing the subject to sports. But in NASA's control rooms, this isn't awkward, it's exhilarating. Because understanding the horizon means understanding the nature of reality itself. The microwave background marks one kind of horizon, the limit of visible light from the early universe. Quasars and gamma-ray bursts extend our reach farther in time, but not past that limit. Webb pushes the boundary toward ionization, but not beyond. Every telescope is a probe against the horizon, pressing it, testing it, but never crossing it. Some scientists speculate about what lies beyond. Perhaps the same structures continue endlessly. Perhaps the physics is different. Regions where constants vary, where stars never form. Or perhaps the universe is finite, curving back on itself like a sphere. Historians still argue whether the universe is infinite or finite but unbounded. Current data leans toward flatness, suggesting infinity, but the margin of error leaves room for other shapes. If it's finite and curved, travelling far enough in one direction could, in theory, bring you back to your starting point, though expansion makes that impossible in practice. It's the ultimate cosmic treadmill. And then there's the multiverse possibility, which we brushed against earlier. Beyond the horizon could lie other bubbles entirely, disconnected from ours. If so, the horizon isn't just about light. It's about universes brushing elbows unseen. NASA won't claim evidence for that, but the speculation lingers in the silence beyond the data. So as you sit with this thought, remember, the edge of the universe isn't a cliff, it's a horizon. A circle of vision defined by time. You're not trapped in a snow globe, you're standing on a shore looking across an ocean whose far side you'll never see. And maybe that's okay, because within our horizon lies enough wonder to fill countless lifetimes. Galaxies upon galaxies whispering their stories across the dark. And if you ever feel frustrated by limits, consider this. The horizon is not the end of curiosity, it's the invitation. Every photon NASA catches, every arc of lensed light, every smudge of a distant galaxy is a reminder that while we can't see everything, we can see enough to know the story is bigger than we imagined. You're still standing at that cosmic horizon in your imagination, staring out at the limit of what can ever be seen, when a darker thought creeps in. If the universe has a horizon, if it has a beginning, then surely it must have a future, and futures, unlike horizons, don't just hide from view, they're inevitable. So what happens when the lights finally go out? NASA scientists have wrestled with this question for decades, and while no answer is final, the possibilities are as dramatic as any science fiction ending you've ever read. They usually boil down to two contenders, the heat death or the big crunch. Let's start with the heat death. No, it's not a heavy metal band, though it could be. The heat death scenario comes from thermodynamics, the study of energy and entropy. Entropy is a measure of disorder, and the second law of thermodynamics says entropy in a closed system always increases. The universe, being the biggest system of all, is on this path. Right now, stars burn hot, galaxies collide, black holes feed, and energy flows from hot to cold. But eventually, all differences smooth out. Stars die, galaxies drift apart, and energy spreads thinly and evenly until nothing more can happen. It's the cosmic equivalent of a party winding down, the music fading, the guests leaving, the balloons sagging. Historians still argue whether heat death is the right term, because the end result isn't hot, it's cold. The cosmos would expand so much that temperatures everywhere would approach absolute zero. Black holes would be the last holdouts, slowly evaporating through hawking radiation over unimaginable timescales until even they fizzled away. What's left? A dark, empty universe filled with nothing but thin gas, stray photons, and the memory of everything that once was. It's the quietest apocalypse you can imagine. No bangs, no fireballs, just this gradual dimming of all light. Here's the quirky tidbit. Scientists have calculated that the full heat death, if it comes, would take trillions upon trillions of years. That's longer than the current age of the universe by factors so ridiculous they make your head spin. If you think waiting in line at the DMV feels eternal, try imagining a trillion years of cosmic boredom. On the bright side, you personally won't be around to suffer through it. Now, contrast that with the big crunch. This scenario comes from gravity's pull. If the universe's expansion were to slow and reverse, all galaxies, stars, and planets would eventually collapse back together. Imagine pressing rewind on the Big Bang. Galaxies racing inward, heat rising until everything smashes into a singularity again. Some theorists even speculate that such a collapse could trigger another bang, a cycle of expansion and contraction, universes reborn endlessly in a cosmic heartbeat. Historians still argue whether ancient Hindu cosmology, which spoke of cyclical universes, eerily anticipated this model, or if it's just a poetic coincidence. For a while, the Big Crunch seemed plausible. After all, gravity pulls inward. If there were enough matter in the universe, it could overcome expansion. Astronomers spent decades trying to measure the critical density, the tipping point between endless expansion and an eventual collapse. NASA's satellites like WMAP and Planck mapped the cosmic microwave background with such precision that they pinned down the answer: the density is too low. Expansion isn't slowing, it's accelerating thanks to dark energy. That makes the Big Crunch unlikely. Still, some fringe theories allow dark energy to flip in behaviour someday, turning from push to pull. If that happened, the crunch could return to the table. Let's pause for humour. One science writer once described the heat death as the universe dying of boredom, and the Big Crunch as the universe committing suicide. Neither is cheerful, but they do capture the vibe. Imagine sitting through the heat death, stars slowly winking out, galaxies disappearing beyond horizons until you're left with nothing but a cold expanse. Now imagine the crunch, galaxies careening inward, temperatures rising until space itself collapses in on you. Take your pick, slow fade or dramatic finale. Historians still argue whether there might be other endings too. One idea is the Big Rip. If dark energy isn't constant but grows stronger over time, it could eventually overwhelm even atomic forces. Galaxies would be ripped apart, then stars, then planets, then molecules, until even atoms were torn asunder. A universe shredded into its fundamental particles. On the opposite extreme is the bounce, a variation on the Big Crunch where collapse leads not to annihilation but to rebirth, a new Big Bang sparked from the ashes of the old. This cyclical model paints the universe not as a one-way story but as an eternal loop. NASA, of course, doesn't frame its missions as doomsday forecasts, but by measuring the rate of expansion, the distribution of galaxies, and the properties of dark energy, it's quietly helping us sketch the universe's obituary. Missions like Roman are designed not only to map dark energy now, but to ask how it might evolve. If it's truly constant, the heat death is our most likely fate. If it changes sign, the crunch or rip could emerge. Imagine a detective piecing together not just a crime scene, but the victim's entire life story, including the ending. That's cosmology. Here's another quirky tidbit. When asked about the universe's end, some astronomers can't resist gallows humour. One once quipped, "Don't worry, it's not the end of the world, just the end of all worlds." Another added, "If you're still around for the heat death, bring a sweater." Even in the face of ultimate nothingness, scientists lean on jokes, because really, what else can you do? You close your eyes and try to picture both scenarios. In the heat death, stars fade one by one, galaxies slip beyond sight, black holes hiss faintly then wink out. The universe cools into silence like the last note of a symphony held too long until it dissolves into air. In the Big Crunch, the opposite happens. The sky grows brighter, galaxies streak inward, radiation surges, heat climbs, until the cosmos itself collapses in fire and fury. Both are terrifying in their own ways. Both remind you that the universe isn't static, it has a trajectory. And maybe that's the humbling part. The cosmos doesn't owe us permanence. We live in a temporary moment, tucked between the bang that began it all and whatever silence or fire will come at the end. Historians still argue whether contemplating the universe's death makes life feel more futile or more precious. Perhaps it depends on your mood. For some, it's despair. For others, it's liberation. Knowing everything ends makes every sunrise, every galaxy, every heartbeat more miraculous. So as you sit here tonight, wrapped in the story of the cosmos, think of the universe not as eternal, but as evolving. NASA hasn't just shown us where we came from, it's hinted at where we're going. Heat death, Big Crunch, Big Rip, Big Bounce. Take your pick of finales. They're all beyond your lifespan, beyond your species' lifespan, but not beyond imagination. And maybe that's enough, to know the story has an ending, even if we won't be there to read the last page. You're still lingering on the cosmic question of endings, heat death, Big Crunch, Big Rip, when the thought shifts from how it ends to what comes next for us right now. Because if NASA has taught us anything, it's that we're not content to just sit and wonder. We build better eyes, better machines, and we point them skyward. The universe may have its own fate, but our story is about seeing as much as possible before the curtain falls. And right now, the stage is being set for NASA's next generation of future eyes in space. Start with the Nancy Grace Roman Space Telescope, often called Hubble's wide-eyed cousin. While Hubble zooms in like a telephoto lens and Webb peers deep in infrared, Roman is designed for the big picture. Its field of view will be 100 times larger than Hubble's, letting it survey vast swathes of the sky in one go. Picture Hubble as a photographer crouched in an alley, and Roman as someone flying a drone over an entire city block. Roman's specialty, mapping dark energy, dark matter, and exoplanets through micro-lensing events. Historians still argue whether it will deliver a decisive answer about dark energy or just sharpen the mystery, but either way, its wide view promises to reveal the large-scale architecture of the universe like never before. Then there's LUVOIR, the Large UV Optical R Surveyor, one of NASA's concept megatelescopes. Imagine Webb, but on steroids, a mirror up to 15 meters across, dwarfing Hubble's 2.4 meters. LUVOIR would be capable of directly imaging Earth-like exoplanets, studying their atmospheres for biosignatures. Think oxygen, methane, maybe even smog from alien traffic jams. It would also probe galaxies with unprecedented clarity, pushing closer to the very first stars. Quirky tidbit, LUVOIR is still in the drawing board stage, but some scientists already joke that if Webb is the James Bond of telescopes, LUVOIR will be the entire MI6. Another contender is HABEX, the Habitable Exoplanet Observatory, a smaller but focused mission aimed at finding Earth 2.0. HABEX would use a giant starshade, a spacecraft flying tens of thousands of kilometers away shaped like a giant flower, to block starlight so the telescope could see the faint glow of planets around it. Imagine holding your hand up to block the sun so you can spot a firefly in daylight. That's HABEX's entire trick scaled to interstellar proportions. NASA engineers have already tested starshade prototypes on Earth, and yes, they look like giant origami daisies drifting in space. Historians still argue whether HABEX or LUVOIR will win the funding battle, but the dream is the same, catching a glimpse of a pale blue dot circling another star. And don't forget the Origin Space Telescope, another concept mission. Its job would be to probe the cold universe, dusty galaxies, hidden star nurseries, faint chemical signatures that Webb can't quite catch. Origins would be the forensic scientist of the fleet, digging through cosmic ash and residue to reconstruct how galaxies grew and planets formed. If Webb is about fireworks, Origins is about fingerprints. Here's a quirky tidbit that gets less attention. NASA is also dreaming of probes beyond telescopes. There's the idea of a solar gravitational lens mission, sending a spacecraft out to 550 astronomical units, so far away the sun itself becomes a natural lens, magnifying distant exoplanets a billionfold. In theory, you could get images of alien worlds detailed enough to see continents, oceans, maybe even city-dots if they exist. Historians still argue whether such a mission is technologically feasible in this century, but it's the kind of audacious plan that makes you giddy. Imagine the sun itself as your telescope, bending light like the universe's own magnifying glass. Of course, NASA's future eyes aren't just about big, flashy flagships. Smaller missions, like the spheric satellite set to launch soon, will scan the entire sky in infrared, cataloguing hundreds of millions of galaxies and probing inflation. Think of it as the cosmic census taker, less glamorous than Webb, but just as vital. Together, these missions will weave a tapestry, each filling in gaps the others leave behind. Let's pause for humour. Astronomers sometimes call this future fleet the Dream Zoo, because each proposal sounds like a different animal. Roman, the wide-eyed eagle, LUVOIR, the giant elephant, HABEX, the starshade flower, Origins, the mole sniffing through cosmic dirt. You can almost imagine a NASA brochure. Come visit our zoo of telescopes, see the giant golden mirrors, the space flowers, the infrared hounds. Somewhere an engineer is rolling their eyes, but the metaphor sticks. What unites them all is ambition. Hubble showed us galaxies where we thought nothing existed. Webb is showing us galaxies that shouldn't even exist yet. Roman, LUVOIR, HABEX, Origins, they're about pushing the questions even further. How did the first stars form? How does dark energy behave? Are there other Earths and are they alive? Each telescope is a new pair of glasses, a sharper lens against the horizon. Historians still argue whether we'll ever reach a point where telescopes can't improve, where the universe's faintest whispers slip forever beyond detection. But if history teaches us anything, it's that every time we think we're at the limit, NASA builds another machine and proves us wrong. 100 years ago, Edwin Hubble needed a ground telescope the size of a garage to see a smudge called Andromeda. Today, NASA's instruments catch galaxies from 13 billion years ago. tomorrow, who knows? You lean back and picture this cosmic relay race. Each telescope hands the baton to the next. Kobe mapped the baby glow. WMAP sharpened it. Planck polished it further. Hubble showed us the deep fields. Webb is revealing the ancient dawn. Roman will map the scaffolding. Louvois or Habex may catch Earth-like planets. Origins may reveal the hidden chemistry of dust. It's not one telescope, but a lineage, a dynasty of eyes, each widening the horizon a little more. And here's a comforting thought. While the universe may one day fade into death trillions of years from now, we, in our little moment, are doing everything we can to see it, to understand it, to tell its story. The cosmos may not care, but we do. And that matters. The next time you hear about NASA's future plans, don't think of them as cold machines or gadgets on spreadsheets. Think of them as gifts to curiosity, golden mirrors, star-shaped shades, orbiting eyes that will outlive us, carrying humanity's questions farther than we could ever go ourselves. You've walked through the cosmic web, brushed past quasars and gamma-ray fireworks, peered at the faintest galaxies, and listened to the universe's whispers of dark energy. You've weighed futures of heat death and big crunch, and glimpsed NASA's next generation of golden eyes, preparing to stare deeper still. But now the telescope turns back gently toward you, because the ultimate discovery at the edge of the universe isn't just galaxies or equations, it's the perspective they give us about our own small place in all this vastness. Let's put it plainly, you are tiny. Your entire planet is smaller compared to the Milky Way than a grain of dust floating in a cathedral. And the Milky Way is itself only one of hundreds of billions of galaxies in the observable universe. Statistically, you shouldn't even register. And yet here you are, able to think about it, to build machines that pluck ancient photons out of the dark, to laugh at nicknames like cosmic horseshoe and naked eye burst. That paradox, insignificance paired with awareness, is what makes this journey so extraordinary. Historians still argue whether looking at the cosmos makes people feel humbled or empowered. Some say the immensity proves our lives are fleeting accidents. Others insist it does the opposite. That awareness of the cosmos gives meaning to our brief moments, like fireworks all the more beautiful because they fade. NASA doesn't settle that debate, it just hands us the data. The interpretation, the meaning, is up to us. Here's a quirky tidbit that shows how humans process the cosmic scale. When Hubble's first deep field image was released, some people said they felt dizzy, even nauseous, staring at so many galaxies. One therapist even reported patients describing existential vertigo. On the flip side, others framed the photo and hung it on their walls, using it as a daily meditation, a reminder that traffic jams and missed emails shrink to nothing under the stars. The same image, two opposite reactions. The universe is a Rorschach test written in galaxies. You picture yourself again, lying back in bed as the story winds down, imagining the night sky above. Every star you see is local, part of the Milky Way. Every galaxy you've heard about here is invisible to your naked eye, faint smudges caught only by the patience of telescopes. And yet your brain, sitting inside a skull not much bigger than a melon, can hold the whole picture. Big Bang, Dark Ages, Cosmic Dawn, expansion, acceleration, ultimate fates. The neurons firing in your head echo the patterns of the cosmic web. Tiny sparks, infinite reach. Humor break. If aliens are out there listening, they might find it funny that one of our species' greatest achievements is pointing giant mirrors into the sky, just to confirm that we're not the center of everything. Imagine a galactic travel brochure. Humans, tiny, anxious, but very good at building cameras. And yet that humility is beautiful. To know we're not central but still curious, still reaching, that's our cosmic signature. NASA's findings at the edge of the universe boil down to this: there's always more. More galaxies in a grain of sky, more mysteries in the microwave hum, more puzzles in dark energy's whisper, more fireworks, more webs, more horizons. The universe is a story without a final page, at least not one we'll ever read. And somehow knowing that makes your own page in the book feel richer. So the edge isn't a wall, it isn't even a finish line, it's a mirror. When you stare far enough out, you start to see yourself, tiny, fleeting, yet capable of awe. The same awe that made NASA engineers launch billion-dollar telescopes. The same awe that made Edwin Hubble scratch his head at redshift graphs. The same awe that made you press play on this sleepy story tonight. And if the universe does end someday, whether in heat, crunch, or rip, let this sink in. Right now, in this fleeting blink, you're part of it. You're listening to echoes that began before Earth existed. You're alive in the only corner of time we know consciousness has bloomed. That's not small, that's astonishing. And now, as we let the narrative settle, it's time to soften everything, slow the pacing, and let your mind drift. The telescopes can rest, the galaxies can fade, and the universe, for tonight at least, can grow quiet again. Imagine the sky above you not as a place of questions, but as a vast, calm ocean stretching endlessly in every direction. The noise of debates, heat death or big crunch, quakebars or multiverse, fades into a gentle background hum, like waves on a distant shore. The mysteries are still there, but they no longer press urgently. They wait patiently the way the stars have always waited. Your breath moves in rhythm with that ocean, slow and steady. The rise and fall of your chest mirrors the expansion and contraction of galaxies, the pulse of the cosmos at its gentlest scale. Every inhale gathers starlight, every exhale releases it back, as though you are both observer and participant, woven into the same fabric as the stars themselves. Even the farthest galaxy, faint and red on Webb's gold mirror, feels close now, not distant, not unreachable, but a quiet companion glowing softly at the edge of your thoughts. You don't need to solve its mysteries, you only need to let it drift, a lantern in the dark, guiding your imagination towards a rest. So as you close your eyes, let the universe shrink to something intimate. The weight of your blanket, the sound of your breathing, the stillness around you. The cosmos is vast, but your place in it is gentle and safe. You are small, yes, but you are here, and that is enough. Sweet dreams, traveller.